Hello everybody, how's it going? Hey there Akras, hey there Glorious Sun, hey there Sully, how you doing? Hey the Machine Knob, how's things been? How you guys doing? Oh, we're in the right folder. Right, so today is an exciting day. We're getting started on some 3D graphics R&D. It's going to be pretty sweet. So we've now got like a custom UI. With like list views, scroll views, and you know, we've got like a good solid foundation now for like a game engine. So we kind of need to, well, the next thing I want to work on is basically doing some 3D graphics, and kind of find the art style. Just try and find something that's kind of different. So this is what we're going to be working on for the next few weeks, I reckon. Just what can we do to sort of stand out, I think. Should be a good idea. And see if we can get some interesting sort of effects and stuff. So I want to start off quickly just by double checking. I think I might have got my sRGB/linear space thing wrong in my UI. So I quickly just want to set up a debug thing and just to double check that. So I think the sRGB conversion is fine, but I think the problem is like when I provide the colors to the system, I'm providing them as sRGB, but they've been used as linear. So we want to make sure that the user that provides colors is in sRGB space, I think. So I just want to quickly double check that, and then we'll get cracking. What kind of game are you planning on making? Not sure yet. Because every time I think about a game, too early, by the time I get to making the game, I've forgotten enough about it, or I don't want to make it anymore and I find something else interesting, right? So what I want to do is so what we're doing is we're building up like a solid foundation, right? So we've got like OS abstraction, right? We've got this thing, so it's got like gamepad, it's got like keyboard, key code there, keyboard, mouse, gamepad. We've got like a GPU thing now. Oh, yeah, one of them. We've got a UI library thing. Now we've got like our own sort of, custom like core sort of memory utilities. So the engine is now in a state where I can sort of prototype 3D graphics, right? Basically. And then after we've got our 3D graphics, I think we've got enough of a foundation to be like, right, we could now prototype some game ideas, or we could, so first of all, have maybe like a few games that we can think about. Maybe some of them will need prototyping, so we've got a solid foundation to probably prototype some basic ideas. And then you just go from there, really. That's the plan for now. Because when I want to do the game design, I want to sort of really focus on it, I don't want to just like think about something and be like, oh, this thing's amazing. Write the core part of the engine, and then by the time I get there, it's just, I've forgotten about it enough. Where it's, so yeah, we'll get to the game very soon after we've done all the 3D stuff. Exactly. Yeah. Many times I've done that and I've just lost the idea, and it's like, well, yeah. You need to focus on things, right? If not, you won't get things done. Like we're focused enough, we've got UI done. Obviously, right? The game is obviously the UI is not like completely finished. We're gonna have to come back in and do little bits. But that's where I hope to get the game design, right? I hope to get it done enough where I just have to come in and do little bits. And if I change something, it's not going to sweep the rug out of the whole core idea of the game, right? So we're just building on top of it, right? That's where I want to get to. Hey, they're not so red. Things going good, man. Things going good. How you been? How's things going with you? Have you Have you started your internship yet? So the thing I wanted to test is I wanted to go into the graphics thing, right? And I want to disable, well, okay, in main I want to disable this UI stuff, so we're just rendering a black screen, right? Perfect. Just what we like to see. Now, I want to set up a for loop. Here's one I made earlier. And I want to render a bunch of these guys. Boxes. And they've got to be a solid color. And we're going to just test to make sure our sRGB is on point, right? The colors that we pass in shouldn't be they should be in sRGB space, I think, right? And not in linear space. And I think this is a problem with the UI renderer, is it's not converting from sRGB to linear. So we're just going to just quickly test that out. I think I got it wrong. So do some bars, right? We'll just do vertical bars. So that one, we'll say it's 55. Yep, so 150, half size. Oh, half sizes. Good point. And solid color. So it's something like that. And we want to increase in gray, basically, isn't it? So we want to do 1 1 1 1. Yeah. 0 0 0 0 0 0 plus 0x 0 0 1 1 1 1 1 1 times x. Right, we'll call it like step, or not step, no. Scale. Let's just call it SSS. Yeah, so we're just gonna get basically across the screen a bunch of gray bars, and we'll be able to tell if this is in sRGB or linear, effectively, and it'll get more and more, it'll start off as black and go to white. So we'll start, this needs to be half Y. Right, that ought to be good enough. I just got to make sure this is a good increment. 1280, isn't it? Yeah, divided by 16. 80. 80 pixels. 80. Half of 80 is 40, and voila. So let's give that a go. Wait. SSSS. Why not C++? Because there's too much PP on the C. Sully. Rust. Yes, we could have done Rust. That is true. Shoot, I didn't offset it enough. But yeah, I think this is a good test. Yeah, already started. Sweet. Good stuff. I could have done that, isn't it? Yeah, I could have done it in code rather than the calculator. I know, right? Or I could have just been smart enough and used my brain, but my brain don't work that well. So with linear and sRGB space, like you should see, maybe we need more, should we, maybe we need more, so I'm not sure if this is correct, actually. That's not correct, that's why. The number's wrong. And also this should be offset by plus 40. Yeah. Let's flop out the hex calculator. Right. So all the bits. That's the number. Bet like everyone else knew that, you know. Okay. Right, that's the wait a minute. I did divided by 16. That's wrong. Because 16 in hex is, it's 10. Shoot. Of course, well, that's why that number looked wrong. Right, okay. Divided by 10, which is 16. Sure, I guess that makes sense. Oh, damn it. Right. So of course it looked wrong. Okay, so 1, 2, 3, 4. Excellent. Apparently not. Yeah, of course it would just be 16 because you're timesing it by I'm confused. How's that look? Right, that looks better, doesn't it? It goes from black to white. Is that fully white? That's the question. Like, yeah. So we want to tell, like, so if we get a picture up, we should be able to tell linear versus sRGB ramp. Right. Yeah, so if it's linear, it's more like this. I'll move this over because you guys probably can't see it too well. You know what? Google in the year 2000 was far better because you could use to press a button. I'm not sure if people remember this, and it takes you to the full image. Then you have to get an extension now to do it. Right, so the idea is we should be seeing this and not this. And by the looks of it, we're seeing this one, right? So we're going to do the sRGB conversion and just to double check it, right? So if we hop into the shader, okay, because the reason why I wanted to get this right is because when we're doing the 3D stuff, I want to make sure that, you know, we don't fundamentally mess something up, and when we do like proper colors or something, you know. So yeah, because I was thinking about how I'm gonna do this, like what I'm gonna do for this 3D R&D, and I was like, okay, it needs a color, and then I was just reminded of like, hang on a minute, we don't do like what space is the coloring that we pass in, and I don't think we changed it. So here's where the color comes in. So should we have to say sRGB? Because right, so this source color is in linear space, right? Because when we sample from a texture, we convert it from sRGB into linear. And then at the end, we go from linear to sRGB space, right? And then store it into the texture because the texture wants it in sRGB. So we weren't doing, I've not been doing that with the color that comes in from the CPU side. So it makes sense. sRGB or linear to sRGB. Something like this exists. Fast 4. Fast 4. Right. So Now if we look at the ramp, it should look different. I can't tell. Solid color. It does look the same. It's weird. Did it get compiled, right? So let's make it all white. And let's just make sure this code is actually being called. Right. Sorry for people's eyeballs there. I should have done all black, but we had to know the answer. Hey, Egotist, how's it going? Is it something up with my function? So let's do sRGB. Wait, we should have done sRGB to linear. That's why. sRGB to linear. Yeah, so just made it more linear, which is obviously not linear. Yeah, put it more in that direction. I don't know. I think we need more. It's better off if we take a screenshot, isn't it? Right, let's get the old one. Is there a way where we could... There's not a way where we could make it flicker or anything, because I've got a time variable. So what we're gonna... And I don't have hotcode reload yet. So we're just gonna do the lovely if zero else end if. Let's just make... So we're gonna take a screenshot. So this one is the sRGB converted one. Oh, Temporis. Genius. Genius. If that is a genius move. Where is it? Oh, I did something silly, isn't it, with a pixel coordinate. Right, that's fine. Pixel coord.y, if that's greater than 960 divided by 2. Yes, I'm doing this. My brain is not cut out for this maths today. And I did just copy and paste that. Oh yeah, one of these. Ooh. Oh yeah, I think I have dims actually. I have the dims, isn't it? Damn it. I think you guys should just take over and program, you know. Could you do it all right? It's finally getting cold here, so I don't have to listen to my PC fans. Excellent. And now the PC fans are contributing to the warmth of the building as well. Why aren't we seeing any difference? Is my conversion function like this should be? And I need more of these, you reckon? Let's try more of them. Either I'm not understanding the whole sRGB thing, or one of my functions is wrong. What if you did the else branch? What if you do in else branch the other conversion? Oh, right, the linear, yeah, did the other way around. Yeah, interesting. Yeah, something's fishy. Like, let's just make it black, right? Let's just start simple. Right. Code works. Why do I use Brave? Because it's got an ad blocker. And I like to take away people's earnings. No, I'm joking. Ads just ruin the internet. I don't like whenever you use any other browser, just the internet is just terrible. Hmm. Right. Right. So why are they the same? Right, so let's add more steps. That's the next thing we'll try out. So let's add, should we add, let's do 64. Wait, 64 ain't 64. 2 seconds, gotta hex this. 40. Right. So obvious when you do it. Okay, divided by 40. That's the number. So that's our step. 1, 2, so 1, 2, 3, 4. What? Yeah, that's right. So we're doing how many steps? Mm-hmm. 20. Ten pixels apart. Sorry, 20 pixels. 20 pixels wide. Excellent. Right. So we're seeing a difference now. Right. Those. Why do those go more blue? Okay. Here we go. So SR. This what we shouldn't be you doing this right. This is wrong, but it was a good test just to see that it's different. This is what we should be doing right from S. The color that's coming in is in sRGB to linear. That's what I'm thinking. So, right. What could it be? Why is it blue? That is the question. The top one is this one here. I'm not Trocacoon. Are you making a game? At some point, we're going to do some 3D graphics. We're starting that today. Oh, 16 steps, that's why. Right. It's 80. Eighty is 16 steps. Oh, wait, no, I've changed that, right? Yeah, I changed the numbers. Hey there, Drago. Thank you so much for the raid. Appreciate it, sir. How you been? How did the stream go? Yeah, all code. No worries. No worries. Right, so we are using the fast function. I'm confused now. We must get to the bottom of this. Let's try the more... Well, there is the correct ones we've got down here. Right. So we know linear to sRGB works because we use that one already. And hang on a minute. We know we do texturing and we do linear sRGB to linear anyway. And we know this one works as well. Because well, I've got an image that we've seen and it looks good and it looks fine. So what? Oh, it looks blue because 1, 2, 3. Yeah. Wait a minute. It's not grey. Yep, so 64 is not, like, this is a 3, isn't it? You want this to be like a... yeah, it's backwards. So it's R, yeah, it's B, G, R. So the B is... Yeah, there's something definitely wrong with it. So we need to find a number that's divisible by something. So if you divide by 16, you get that number, and it's F, 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 F. We need another number like that one. So 30, oh my days, 20. That's not good. So we knew 30 wasn't right. 40 is not right either because it's that. So let's try 50. No, not right. Actually, that's fine because it's even across all of them. Is that right? Because it's even across all of them, it will remain grey, right? This is right. I hope at least. Divide by 256. Maybe that's a good one, isn't it? Yeah. What's 256 in hex though? That's FF, isn't it? Or 11100. Yeah. Right, let's try that number out. That's a good number. Right. 1 byte, 2 byte, 3 byte. Perfect. Perfect. Could you do literally that divided by... Yeah, I think this is right. Yeah, I think this will do. I think it's a very similar thing, Glorious, that you landed on. How many steps we got now? 1280. Decimal, please. Oh wait, 256, right? No, 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 no. Oh, it is 5. Yeah, sorry, yeah, 5. Which means 2.5 here and here. Right, let's try that out. Why they go blue? Why they go in blue? What is going on? Is it the way I'm stepping is not linear, is it? It's, sorry, it's not going... I'm doing something clearly wrong with this, I reckon, like the numbers. So let's just get this in the clipboard. It was that, right? So we did like times... Yeah, it goes like that, isn't it? So it's not really... Do times 3, it's not quite... Yeah, so Glorissa was saying... See, why don't we just repeat it across the whole... So we know we're going 2, 5, 6, so I'm just doing this bit wrong, isn't it? So we just want to repeat that. FFF. Yeah, so I guess we'll just say, like, basically all that with this shifted left by 8, or with that shifted left by 16. Right, and that'll get you grey in all the that'll get you the same value in all the channels, RGB. Or maybe it was the plus here or something. No, it's probably the... Maybe that plus wasn't helping out as well, actually, thinking about it. Let's try that out. Right. This is what we wanted the whole time. Okay, so this is what we have been doing at the bottom. And this is what we should be getting, right? At the top. There we go. Oof. So at the bottom here, this is the bottom one. We've just been doing that. We've not been doing this, right? So the user from the CPU side provides a color in sRGB space. But really, so we should be converting it from sRGB to linear, right? Because at the end, when we throw it back out to the texture, we're taking it from linear space and turning it to sRGB, right? Same with a texture. When we read a texture in, we're taking it from, here we go, there's color, then we turn it to sRGB to linear so we can work on it. And that's what we're missing. Okay, so I'm glad that we actually found the problem and got to the bottom of it. Thank you so much for your help, everyone. That was good. So we're just going to punch these around in every place where we need to throw them. So if we just go into UI or UI.h, what we'll find in the draw code, draw color, right. So we just got to find these guys are taking colors. So solid we've just done. There's bordered, it's got 2, right, that need adjusting. Okay, that's super good. Then we've got texture, which we should have already done. Yeah, it's already done. Texture oh no, that's the same one. Glyph, I think we did glyph. Right, because glyph is just an alpha. That's fine, that's not in sRGB space. Gradient has a couple of colors. These need changing. So that's why the gradients might not have looked as good, actually. We should re-enable the other test scene and just take a look at it, see how much different it looks. Right, so gradient linear. Well, we've got the colors, right? Here. Let's plop those in. And these ones here, plop these in here. Okay. Oh yeah. Gradient distance, there's a color, there's another color. Right, that's it. Right, so there's a test scene. So let's get rid of this test scene. So that was a nice little test. But there's a test scene. So this is the buttons. Let's see what the screen of buttons looks like now. Well, why isn't it rendering? Oh, because there's a 0 here. Right, don't really look too different. Excuse me, probably because they're fully on. Yeah, they look about the same, I think. But let's do something where it's not just like, well, I don't know, maybe the colors we've selected are not that good. Test subjects. Man, this is hard to figure out. So that's LF. Okay. Here we go. Right, so this is it properly adjusted now. I don't know if I can see too much of a difference. Would have to undo the code and take pictures. But these gradients probably look better here. I'm not sure though. I'm not sure so much about these. Because the problem is if you have something that's like fully blue or fully green, I don't think it really affects it. It's more of how the color ramps act, right? That's mainly what it is, how the color ramps are acting. They're more smoother rather than being very, they just happen all of a sudden. Oh, look at those count. Okay. Right, so I'm glad we sorted that out. So let's check that in, and then we'll get started on the 3D R&D stuff. Take a look at this. I shall. Yes, as you've seen, if you work in this space, it just instantly basically turns white, whereas this one's more, the perception of it is more gradual, right? Even though it's exponentially, is that right? Yeah, this one is, yeah, it's kind of weird, right? Like, you expect this color space to look like this one, right? Because it's called linear, but really, your eyes are really affected by, they perceive light. Yeah, like this is as you can tell, this here gets sort of like, this tiny space here is like stretched out all along here, essentially. It's it's weird. Alright, let's take a look at this thing. Oh, my eyes. Poor man's color grading before and after. Yeah, you can see like the banding, isn't it? Yeah, this one. Very blinding. I'm trying not to look at the middle. Maps infinity. So it's linear, infinity to positive one. Yeah. Okay. Excuse me. Yeah, well, this looks more like a sun, I guess. If you had it in the sky, right? Because you can see the outline of it. Whereas this one is probably more correct if it's something that's... What am I trying to do? Oh, we've just fixed my sRGB stuff in the... We'll just start off by fixing my sRGB stuff. Most of it was correct. The problem is the colors that we passed in from the CPU were not doing the conversion to sRGB to linear. So we've just fixed up that, and that was the warm-up today. But yeah, right, so let's get that committed and then we'll get started. Right. Correct sRGB, correct UI colors coming from CPU not being converted to linear from sRGB. Oh yeah. So we're doing 3D graphics with compute shaders, compute shaders. So there's a few sort of primitives out there, and there's a few different ways you can render things, basically. So let's get Milton out. Good old Milton. So the classic way, right, when this thing loads, it's got to boot up Wine, and then we can finally load the application. Oh, there we go. So the classic primitive everyone is used to is the triangle, and effectively it's you use triangles to model the surface of a use triangles to model the surface of an object, right? And you can make all sorts of things out of them. You can make like, yeah, all sorts of things. You can make like a mesh, right, of these guys. So computers are really good at doing these things, but we want to kind of not do triangles because I want to try and get something more unique as an art style, basically. So I think if I do a different primitive, I'll get that right. Obviously, there's a lot more things you can do to make your game look different, but let's just start at right at the core of it. So the other sort of alternative you can do is voxels, right? It's meant to be a cube, but then my hand can draw a cube. Is voxels. So voxels are kind of cool. You know, obviously they got really popular since Minecraft. And you can render them with compute by doing ray tracing, right? But the problem with voxels is if you try and animate voxels, there's a few ways you can sort of try to do it, but it's very difficult. And you can effectively do like sprite sheets in a sense, but on 3D, right? You can do like where you flip between different voxel, where essentially it's like a sprite animation but with voxels. Or you can try maybe sort of like you have your voxel and you have a ray that comes in, you can sort of like distort the ray a bit, and which would end up like morphing how this voxel looks, right? But that's a bit, it's got its limitations, right? It's not perfect, but you can make the voxel look different by literally just morphing the ray and stuff like this. And another problem with voxels as well is they kind of take up a lot of memory. If you have them like proper small, it might take up like tons and tons of memory. So I didn't really want to go with voxels either. And they kind of, I think like a year or two ago, I was like, yeah, voxels would be pretty cool to play around with. But yeah, I want to try. That sort of limitation with the animation sort of made me look into different things. So there's another sort of thing you can do, which you see more in movies or sort of like special effects in games. So they're not necessarily used as a primary primitive, but basically what I want to try and work with is a sphere. And I want to try and work with tons of spheres. And the idea, so things might look a bit bubbly, but I'm not sure how big I want the spheres to be, right? So we're gonna effectively render tons of spheres. So the whole objective for the next couple of weeks is figure out, can we render tons of spheres really fast, and what limitations will we have, and also what interesting things can we do now that we're rendering with just spheres, right? And so there's a few ways you can do this. You can ray trace the spheres very easily. What's great about spheres as well is you can actually animate these, right? Because they're just points in space, you could do all of the sort of bone animation stuff you can do on a, you can have you can have your bones effectively, and your spheres will, be, you can do that sort of bone animation stuff still with spheres, since it just points in space. But when you do that, you do sort of get holes, right? But that could be part of the aesthetic, right? But also you could effectively fill up a space with spheres, and then if you sort of bend them, if you've got enough spheres, you won't see the holes, right? So that's maybe a thing we could do. Yeah, I'm not sure if you want to ray march, because ray marching is great for shapes that you don't know, like complex shapes. But spheres are the most simplest shape to ray trace. It's literally a distance check and how far you are away from how big the radius is. It's dirt cheap. So there's a few ways to do it. There's ray tracing, which we're going to start off with, because it's the one that can give us the most good look, and it could be the most expensive. So what I want to do is see how fast we can make that one. We'll probably do a similar thing to what we've done with the UI, basically. And then that'll make me learn about, maybe I can make the UI thing better because I've done this in a similar way. And then the next thing we'll do is do the super fast renderer. And there's ways you can do it with like atomic mins, basically. But people who do research papers and stuff work on pixel-sized points, and you can do like an atomic min on the screen, and it's super quick apparently. But the problem with that is you get like, it might not look good. So what we might do is render these. We might basically do a mixture of ray traced atomic min effectively. So there's two approaches to rendering, right? You could say a compute shader could be like, I'm rendering, I own these pixels and I'm going to render these pixels in this grid, right? And then you have to, per pixel, you iterate over every sphere in this sort of tile. That's the way we're going to start off doing it. But the other way you can think about rendering is my thread is going to render a sphere, no matter where it is on the screen, which means you will get overlap, right? Here's a sphere in here, there's the box for it. Here's another sphere in this box. So what you'd use is atomic min to set all the threading things, right? Yeah. So those are the two approaches we're going to take, and we'll see how good they are. Minecraft but spheres, nice. Yeah, so that's what we'll probably start off with, is like, the way we're going to do it is just basically treat the spheres as if they're on a grid. But then when they get in the world, like they'll be like that in the way this, we'll probably do the custom way to make models. But when we bring them into the world, they can animate differently, they can organically breathe, right, and do all sort of weird stuff that you probably couldn't do with standard things, right? See, I'm not sure what texture them, Glorious, because the idea is they're going to be so small that they are the texture, right? So that's the hope. Yes, you can rain march to take care of the holes. I guess so. But yeah, I'm not sure. Right, I see what you're saying. You can have a bit of a Yeah, I don't know though. Maybe. That's interesting. I'll think about that one as we develop. If the holes become a problem, then maybe we'll think about it. I was thinking of some form of SDF calculated from voxels in sparse voxel tree. Yeah, there is that open is it VDB? Voxel, yeah, this one. I'm not sure if you've seen how the data structure of this, but it looks interesting. Apparently, wait, is this it? Is it VDB? Am I thinking about novel hierarchical data structure? Yeah, I think this is it. There's a sparse volume data structure. If you look at this, it seems quite interesting how this one works. Like, to get to any voxel, it's quite cache efficient apparently. But anyway, take a look into that if you're interested in that sparse voxel tree stuff. I'm not sure if we would need that though. We'll see. Ray marching gives you depth checking for free. Yeah, but I'm not sure what you mean by that. But you can just do a quick ray trace, and it's... You get distance from every pixel, for every pixel. That way you can also make outlines or bloom. Right, so you've got a ray and you're marching the ray. I still don't understand how you get the like ray tracing gets you the distance, right? No, ray tracing isn't an optimized. No, ray tracing is an optimized ray marching. Ray marching, you need to march. Ray tracing, you just need to check. Like, say you have these three objects, right? Here's your camera. Okay. Beep. There's the eye. You you're launching a ray off in this direction, right? In this direction. For ray marching, right, you have to check, like, okay, you start launching it and you go, right, how far is the nearest one of these guys? Right, and you go, well, it's okay, the distance is about this far, right? So I can travel this far and I stop, right? But no, but to do that check, I have to check the distance from this one, the distance from that one, and the distance from that one, right? So it took me 3 checks. Then I have to go and do the 3 checks again. Which one is the closest distance? This one. So I step by that distance, right? Then I go again and I check, right? You see where I'm going with this, right? And then I've stepped, and then I'm, then this is closest distance, and I step, closest distance, and I step. Keep going until I hit the end of the wall or something, right? What ray tracing is you just go, right, I got this ray, this direction, and I go, and I literally can just, like, I can literally just check. Here's the difference between this and the camera position, and I can just check, like, am I, like, wait, is that right? Yeah, I can literally just check. Wait, what's exactly it works? See, it's not at that distance. Put this ray at that distance. I don't think it's that. I forgot what it is, but it might be. Let's just imagine it is. If that ray's at the, maybe the ray goes here. You check if you're inside the point or something. I'm not sure. I forgot exactly what it is. But yeah, there's anyway. We'll just check up the code. But effectively, you're only checking 3 spheres, right? And then you know if you've hit any of them. You know what I'm saying? But yeah. No, ray marching has ray tracing. You just check, does the ray intersect with the yeah, does the ray intercept with, yeah, I forgot the maths exactly. Like, yeah, what's the distance from this to here or something? You get checked by the radius, something like that. And then so there's 3 checks, and you know whether you've hit any of them, and that's it. So ray tracing is actually the cheapest. But ray marching means you can do effects, and you can do it for different shapes, probably faster than if you was trying to have other maths. Like, yeah, you can do really organic-y looking shapes, right? Basically with ray marching. Be away. Yeah, that sounds interesting. Pick a color from the nearest sphere. Yeah, that's quite interesting. Right, so what you're thinking about there, Glorious Sir, is when you start doing lighting and checking the bounce light on rough surfaces. Basically, that's roughness. Well, why did I say calculator? It's not maths. So basically, right, you've got. Wait a minute, when this thing loads. Why do I close this thing? I've got RAM, right? What am I doing? So if this is a rough surface, if you have, like, in PBR and this is rough, technically, it shouldn't be a smooth bounce, right? Technically, it's actually very jagged at the sort of micro surface of here is very jagged. So when you bounce a ray off it, it's actually different. So to sort of simulate it being rough, you effectively pretend to launch many different rays and then sort of accumulate the color, right? And maybe you just these other rays basically look for the nearest lights or something. But yeah, yeah. Then and that's where you're thinking about that. You basically it gets very noisy. So you basically use some people use temporal effects to fix it. I'm not a big fan of temporal stuff, so we're going to try to avoid temporal stuff as much as possible when we do this. Right, so let's get started on a simple shader. So if we go into HTC's samples, what you'll find. So HTC is my custom C compiler for shaders, right? And what you'll find is that there is actually a there's a voxel ray tracer. I just got to figure out how I launch this thing now. How does one run the sample? Oh yeah. Scripts run. Wait, it's in that folder. Is it in the folder? CD samples. Right, here we go. Anyway, so there's a ray marcher, right? It's clearly fabulous ray marcher. Anyway, this is a voxel ray tracer, and as you can see, the voxels are so small that you can't tell they're voxels. You get a bit of like jitter around here. I don't know why that is, but you know, it's not. But effectively, like if you can make the spheres so small, then the texture is the sphere, right? You don't need textures. So the idea is we're going to take this ray marching or ray tracer, strip out the voxel bit and just do it on a sphere instead. And we'll put some spheres out and just get that working. And I'm hoping we can get some anti-aliasing for free. I'm not sure. I'm thinking we can because I've done it with the SDF UI. We basically got anti-aliasing for free. So if we can get the whole world anti-alias with spheres, that would be pretty cool because then we don't have to use any of that multi-sampled anti-aliasing or TAA, which is temporal anti-aliasing. You know, and we can probably just get it for when we just render right up. So hopefully that's the aim, right? Hey there, Gmos, how's it going? Right, so let's go and get this show on the road. So we're in the shaders file where all our shaders live. It just gets compiled. So we'd probably need, right, let's just copy this. So the way I'm imagining I'm going to do it is we're going to ray trace. So let's just get a basic ray tracer shader because I can go write all the code. Sorry, I can go write all the code. But then for you guys, it won't really be the easiest thing to sort of follow. So I'll do it piece by piece. So it's be graphics, compute shader, then we'll say sphere, ray tracer. So we're going to optimize it by breaking into tiles eventually, but for now, we're just going to go over every sphere. So what we're going to do is we're going to have a strut, sphere, and we'll just put them here. So we'll have a, well, three, this is 3D. Position, we'll have a radius, and then we'll also have a color. Remember, it's in sRGB space. We learned that today. But we could probably have more attributes, right? But for now, we've got a bunch of spheres. So we'll define our spheres here. And, you know, we've got array support in HTC, which is pretty fabulous. And then we can just define them here. So we'll put them in the position in world space, basically. Good, how are you? Awesome, good to hear, good to hear. Doing good, doing good. Oh, Pepsi Max. The reason why people are ray tracing is because it's the most physically, more physically precise rendering. What makes a game look good is probably lighting. Lighting is something that makes a render look so much better. Like if you take a look at Minecraft, right? Ray tracing. This thing is literally voxel bricks, right? Voxel bricks. And it makes the world, like when you see like a landscape, this is going way too fast. Right, here's a good example. This thing is literally bricks, and how much better does it look with like good lighting, right? You know, especially when you see a landscape and the bricks get a bit smaller. So like that's why people ray trace, because it look way better. Am I sick? No, not really. I maybe got a little bit of a runny nose, or a little bit of an. I've blown my nose every now and then, but yeah, I'm not. I've come out of a cold, so yeah, I've not got one though. Hey there, Soulfime, how's it going? Right, so let's just start with one sphere, because yeah, one will be good. So we'll position this one in the middle, and then we'll say. So I'm gonna put Z positive, right? I know people put negative for some reason. I don't know why that is, but ours is gonna be our coordinate system, right? Like our UI is X, Y, and then we got Z, right? I'm not sure why the other coordinate systems exist, but we're doing this one. That one. That's what we're doing. It looks much better, but compute much harder. Feels better, man. I don't know. It's more. It feels more like low level and like you're actually doing programming rather than modifying a state machine. Because graphics programming is like, you're just configuring a bunch of state, and then it's like, well, my screen isn't black. But when you start using compute shaders, you realize that you probably get a black screen less, because you're literally controlling, putting the pixels on the screen rather than giving it a bunch of state and then going through some massive machine, like black box machine. So we'll make a red, right? A nice dark red. Because then, right. It's called Milton. Search for Milton. It's actually a Windows exe, but it runs in one just fine. Right, so we're gonna hop over into the HCC test code, and the samples, voxel ray tracer. So this boy here. Right. So we'll plop that down, and we'll see how it goes. We need our own custom constants. Right, so here's our push constants, GFX, sphere, ray tracer. Push constants. Oh yeah, push constants are amazing. So we used to have models, but yeah, we want an output buffer. No printf stuff because we've got that a nice global buffer. Do we want a bit of time? Nah. So we need the dims. Where are my dims? Bam. Right. let's go ham. So we're gonna literally start off. So here's our dispatch. Don't know why I did that in a local. Right. Screen size, that's BC output dims. Right, ray direction for UV. So there's a bit of maths, right? One day, GPUs will be powered by DALL-E Mini and will paint with words. No. Right. So you got your camera, and it's got like a field of view, right? So effectively there's a bit of maths, right? So it's not an orthographic camera, right? It's a perspective camera. So the rays sort of launch out like this, right? So there's a bit of maths that I'm just going to copy and paste from another file. But yeah, it deals with all of that, and it does it in 3D, right? So where's the bugger? So it gives you your ray. This is it. I'll pretend like I know what it does. But yeah, it effectively works off of like the triangle and the angle. But yeah. So ray direction for UV. So we pass any UV in obviously 0 to 1. And we got the size of the screen going in there. And then got the field of view. So we need to probably pass that in at some point. Okay. So we'll say F32 FOV, we'll say 45 degrees, right? A true measurement. Okay, so we get our ray for every pixel, and we've got our ray origin in the world. So this is where we probably want to have this passed in as a parameter, like basically the camera. What is F32? I'm sorry, it's a vector 3 of float 32. Yeah, so it's a way to do all these different types. So you can do like U32 times 3, right? BM. So we probably want to have the camera, like, so you're going to have a camera, and you probably want to have its sort of, where it, its rotation as well. So then it'll rotate the ray, right? So you want the inverse. You're going to do an inverse. Yeah, because something like that, I reckon. But right. So for the camera, at least, like, so these parameters should probably be stored somewhere. But for now, we're just going to put stuff in front of the screen, so it doesn't matter. But we'll put this up here, and we'll say camera. We'll say ray origin, right? Then we'll say camera position. So we'll hard code this, and we'll say to do camera with rotation, or with yeah. So this will probably just be some form of like transform, right? With the whole translation, rotation, and any other stuff you want to do, with a full-on sort of camera defined with a matrix instead, something like that. Yeah, so I've got a custom C compiler shaders. So I've spent like a year writing this. It's called HCC. Oh, you sons of... They want me to do two-factor authentication, which is so annoying. Damn you, Microsoft. SOBs. Right. Okay, so sorry for the white screen. Blame Microsoft. Um, yeah, so custom C compiler compiles it to BAV so we can use it in Vulkan. It's kind of like it does things in a very sort of modern way for shaders. So it does, but yeah, it's got some restrictions. Obviously, it's not full C support, but it's most of the way there. So you can do vertex shaders, fragment shaders, and compute shaders. Push constants are like a first-class citizen. So is this thing called... Yeah, we also don't have don't use like the binding model where you put stuff in a specific slot. It's just passed up as data, right? So you just pass buffers around as data, and you can just use them. So super cool, super modern, and amazing. Yeah. So basically, I can share code between the CPU and GPU, and like I can share structures, functions, and it's super great. Like we don't have to worry about any packing because it's all scalar alignment, even with the vectors. So it's a someone hadn't done it, and I was like, we could have this, so I just did it. So this is part of the reason why we're doing this project as well, is to really test it all out. How long have I been in this field? So I've recently got I've had it in a full-time job about 2 years. So I started it over a year ago. The compiler over a year ago. Right, so this got a voxel model, but we're not doing voxels. Goodbye voxels. So I want to get right. So this is where we need a for loop. So core. What is that in? It's not in shared, is it? Damn it. Right, it's not in my CPU GPU shared code. Cry face. No biggie. Do it the classic way. Wait a minute, can we even do that? I don't know if my compiler supports that actually, because it doesn't support pointers. We shall do it manually. Spheres count equal 1. Spheres count and index plus equal 1. Right. So we'll get a sphere, which we'll call S. Beautiful name. Okay, so your color, what's this color about? This is a load of texture, AABB. Right, we don't need any of that. Right, ray origin, local space. This used to do the sort of rotating. That's how the thing works, right? Because remember in the samples, that rotating logo. But we're not doing any of that at the moment. Then we did the hit code. And then if we hit, we render to the screen. So there's a few things we've got to change. Okay, so we want to do a Rayverse sphere. So hop onto Google. It's probably quite simple. Da, 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 da. Hey Silvercore, how you doing? Yeah, G stands is generics. Yeah, so we get so there's all the generics in C basically. It's using standard C11 stuff. Ray tracing in one weekend. But we want it in one day. How's it going? How you been? Yeah, we should check that out. Returns interval T. Hmm. But yeah, it's probably a good resource because it's like, right. Ray versus sphere. The Ray class. Right. Page down. Page down. Right. Yeah, this is similar to what the other one was. Return. What do we need to know? See, I wonder if we can make it anti-alias for free, because that would be amazing. I think we can. Right, surface normals. Right, let's do this. There's no free anti-aliasing and ray tracing. Damn it. I think there might be a way to do it, right? I was thinking you can do it based on the hit normal, basically. But we'll have to see. Need more samples per pixel, right? Yes, you do 4 samples and then shoot. Damn it. Yeah, we'll see if we can hack our way in. We'll have a think about it when we get the code up. So where's the latest one? What are they doing in the new main? Is the dot here function? They made it C++y? Sphere hittable, here we go. Right, we'll take this and adjust it. Yeah, this got C++y quick. Oh, it's too much PP all over that C. Ugh. Right, let's make a function. Why do people PP everywhere? I don't get it. Sphere. Verse Ray 3D. Oh. Maybe Ray verse Sphere 3D. So Ray is just comprised of an origin and a direction, right? So you basically want effectively Ray origin, Ray direction. The writer is an academic computer scientist. You're 100% going to see one on CPP smeared all over the examples. Oh boy. Yeah. See, I'm too dumb. Okay, I like dumb. Right. And of course, you might be like, where's the sphere stuff? Well, guess what? It's C++. So there's an implicit this pointer all over the place. You just got to figure out which one it is. So is center defined anywhere? Well, that must be sphere center. So, okay. C++. Right, Ray, tmin, tmac. I guess we'll need that. So you want a near and a far plane. Do we? You probably want to near. We'll have it plug in anyway. No doubles. Right, and then you basically want to return a hit. Return like a. What did we call it in the other one? It was yeah, ABB versus Ray hit. Yeah, something like that. So we'll do like a Ray versus Sphere hit. And there's be a bunch of parameters we just return out, right? Oh, yeah. So what we returned for this one at least was T min, T max, and then success. Whereas this one's going to return a. Right, this is quite. Yeah, where you hit at and a normal. We've got to see which ones we want exactly. We definitely want to know if we've hit. So success. We'll get a normal back out. So P, I guess, is the point, because R is Ray at this, so it stepped it, right? T min, T max. So there's a hit point, and what's root? Find the nearest root that lies in acceptable range. Auto. I wonder what this type is. Let's figure it out. So if I look here, you got half B, and half B is another auto, but it's from a dot product, which means it's a float, which means this is a float. But what is this one? It better be a float as well. Okay, it's probably a double, but anyway, float. Divided by A, which better be a float. Direction dot length squared. It's a float, people. We finally decrypted what this is. Please don't do that. Please don't do auto, please. Right, so you've got T. Right, okay, good. Yeah, copied the C++ stuff. Definitely. So it's providing T, but then doing a way of just projecting it across. Right. So what do we want to know? Do we want to know about T? We could know about T. I don't know. But yeah, what you get by default is probably. Oh, but you need. Right, you need P to get the normal anyway. Right. Screw it, we'll return the whole thing. It all gets inlined, it'll get optimized out. There we go, return all that. So let's adjust all this code and get rid of all the C++ stuff. So center is sphere. So we need a sphere to come in. So sphere, I've got to get my sphere class. Oh, it's up there, good. So the sphere comes in, sphere. So we should really call it center position. That is a good good name. So I think we'll adjust that. Okay, so ray origin, well, it's just a variable, so there you go. Ray direction, length squared. Got one of those boys too. So that is len sq f30 times 2 times 3, and voila. So why is there so many autos all over the place? Damn. Just make reading code so hard. So dot product please between OC. So we're going towards there. Oh. Sphere to ray origin vec, something like that. Right, length squared. So that's an optimization, right? We're not doing a square root, which is quite good. Then we're doing radius, that's good. Squaring the radius, it's good code. Right, then you got this one. Interesting. So that is the length squared of that. Right. Should be returning the hit, isn't it? So we'll put this up and we'll say hit. This will say hit dot success. F32. So find the nearest route which lies. Right, so you've got. Yeah, so when you shoot a ray through a sphere, you could end up like before, like, so you have a sphere, right? When you shoot a ray through it, you can know the 2 hit points, the entry and the exit point, basically. So this is what it's figuring out, is which one is the entry point. So right, so you want to do like hit 0. So this makes it branchy. We're going to avoid the branches. And then we'll just do a min, right? Wait, what do we want to do? What do we want to achieve? You want to do a min and then check the bounds, right? So you say hit, say T, and then T, min f equals 2, T0, T1. How does auto work? It might be too much PP for me. Auto works. Auto in C++ is actually really complicated. They've actually done it in C23, but they've done a less complicated version. I cannot explain the rules to you, but effectively, like, if it's like this, it's probably quite simple. It's whatever the expression is on the right-hand side. But you can even do it inside parameters and stuff, which basically makes it like a template. I don't know, it's weird. Yeah, it's called type inference. That's the basic idea of it. Hey, Captain Chica, how's it going? Right, so we should really do another branch check here as well. So this will do another thing like this. And then everything else is hit T, and that'll be T. Hit position will be, it's quite simple to do this. You've got ray, so you've got to add ray origin to the when you multiply the direction, the ray direction with T. Right, that's all it is. And then we can use hit position. So that would be sub. So this is only the nice thing in C++, I guess, is you get to do the operator overloading for this specific case. But yeah. And then Divide sphere radius. So maybe we can... Maybe the divide's fine. Maybe it ain't that bad anymore. Right. So that's the maths you have to do with the ray tracing, which is... Yeah. So... Okay. So you're doing that per pixel for everyone. Oh, wait. Constant override? What is all of this? Ugh. C++. And then return the hit. Right, so that's all the maths we need. We ask for type of, we get auto. Yep. Alongside it, yeah. We ask for defer, we get constant expression. Yeah. Yep. We ask for defer, we get null putter, as the C++ people call it. Null pointer and null pointer t. Why? 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 Null wasn't defined enough, so what we're going to do, rather than make a breaking change, which we did anyway in the spec already, we're going to introduce a new thing called null pointer just for null pointers. Yeah, auto is mostly compile time. In C, it's all compile time, but I think that they're eyeballing some of the C++ stuff. Yeah, which is not good. Right, so ray origin. What's the ray direction? Oh, I've already got that, that's good. Ray direction. Right, it's got Tmin and Tmax. We're just going to assume that they are 0 and infinity, but we should really give these sensible values. So infinity. So to do, make these sensible value. Something like that, right? So so you got ray min tmin, ray tmax, and then we want to just throw in the sphere, and jobs are good. And so what we're going to do is then, if we've got a hit, so this used to then march through a texture because it used to be a voxel, right? A voxel texture, but we're not doing that, right? So goodbye. Now we just need to assign a color. So if we've got a hit, we can essentially just say, right, so we've got a color here. So what should we do? Should we do a return? So we'll say color equals 0. And we'll say color, you know, let's work in the F32 times whatever's, because then we could do some special stuff. And then we'll say, like, I guess we'll put a thing in here and say found hit or something like that. Right. So we'll start this off all at 0. You know what, doesn't matter. Right, so we found a hit. We can do this. Right, so found hit. Yeah, because you might accumulate stuff. Like you could do transparency basically. So we'll just do it this way. Color equal. So we'll do that. Linear. Do we need to do linear from sRGB? Yeah, I think we'll do that anyway. Yeah. Linear. sRGB to linear. And we're converting. You know, I've got to find where we do this. Here's one I made earlier. So the color is sphere color. I think that's good. So we found a hit. We're literally just gonna say, hey, we've got an output texture, and here's our pixel coordinate. Yeah, there's our pixel coordinate, and then here's the final color. Bear in mind the color needs to be converted back into sRGB space. So linear to sRGB. Done. So just gotta get that compiling, then wire it up from the CPU, and jobs are goodin'. Oh, div f32 times 3. Div s. Huh. Ah, me. Thank you so much for the raid, sir. Appreciate it. How's it going? Thank you. How did the stream go? Define you bought unsigned in. Oh yeah. Yeah, it's kind of what Noel's like, isn't it? You say memories. C++ back days make your memory simpler to manage. C++ today. Did you know you can point null pointer to null pointer that points to null that actually does not define null? I'm confused. But yeah, C++ is very complicated. I don't know how Clang made their compiler. That's some solid work must have gone into make that. To implement all that standard. No, I'm not from Birmingham. What are you talking about? Where's my Brummie accent, man? Come on. Brummies. Like, as soon as you go up north to Brummie, they'll be like, oh, I did this, I did. They'll be like, you know, they always have to say, I did. They'll be like, wait, that's a good example. Oh, I smashed that, I did. You know. The fucking streaming mood, yeah. Yeah. And also like the Liverpool accent. Oh my days. Like, oh my days. Yeah. It's insane how different the accents are in the UK. Like you literally just go up north just a little bit and you just go so different. You go up north a little bit more, so different. And it just it's so interesting. It is very interesting. Like, and then you come where I am, right? And then there's different types. You get the chavvy sort of pikey sort of accent. Then you know, to where they sort of like, "Oi, bruv, what you got there?" What, or you know, I can't even do it. But you know, they're just completely different. It's very different, and you're in the same area. Like it's crazy. But yeah, I can't do the accents to save my life. But yeah, should go check them out. Right. We've got a video for it, probably. What is this? Oh, okay. Oh, my days. I gotta get the. Oh. Let's jack up the volumes a tad. Where did the music go anyway? Hmm. Right, swearing warning. Keep your kids away. Maybe that's not quite the accent I was looking for. That went terribly wrong. uh, it is. Yeah, that's not the level. That's not the accent. But yeah. Um, radio. So does it compile? No. We've got a thing called size in here, because it should be dims. Right, let's do that again. Where's the sphere? Oh, right. Yes, to see, guys. So, you know, we've got to do one of these. Vec3, good question. It's that one. Right. So sub f32 times 3. Yeah, so the compiler I've written only does one error at a time. So you don't get a ton of garbage, but then again, you don't get potentially multiple errors that show up. So the problem with C programming is the compilers are like, oh, you got like 17 errors, but then you realize after the first 2, they're not useful. So there's that. Right, then there's a sub here. There's a float, that's fine. Ooh. Why are you complaining? Oh, because it's called center pause. Honestly, with a standard like that, I don't blame the compiler makers. Yeah, I don't know. Like, I wouldn't realize. No, I wouldn't. I don't know where I stand on having multiple errors versus having just the one that comes out. Because you have to hit recompile anyway. Like, but then again, sometimes it does give you the useful ones. So I'm really torn between it. What is this? Do we do a... Oh, it wants to float. Let's do a good old splat. Splat 2. What is going on here? Wait. Oh, nothing called sphere. Right, an S. S. Radio. We're compiling. Is it full C compiler just for Vulkan stuff and the rest? Yeah, it's just for Vulkan, basically. I was hoping to do more targets like DirectX and Metal, but that's... I could do the work, but not be able to test it, so it's not worth doing it yet. But yeah. 1 hour per compilation unit, maybe. Yeah, but 1 hour per compilation unit is what you compile anyway, isn't it? Yeah, I guess yeah. When you have a full build system, yeah. So the compiler itself gives out 1 error, but then the build system reports multiple errors. Yeah. No, it doesn't use LLVM because there's no point. Because SpearV is at the same level of LLVM and it gets optimizations. People seem to think that it's a sensible idea to use LLVM for SpearV stuff, and I've seen a few that do it, and it just doesn't make any sense. Like you might as well just translate into SpearV. It's weird. Right, so we've got this new ray tracer. So what we're gonna do is we're just gonna blast this thing across the screen, and we should see a sphere, right? So here's some UI. We'll do it after the UI, and here we go. Two seconds. Right. So we've got some output, we need some output dims, boom, and that's everything we need. We need to make sure we synchronize on the surface, right? And then we're gonna have on sphere ray tracing. Come on. This does exist. It's code generated basically. It's an enum that's code generated by the HCC. So HCC code gens like an enum for every shader. It also can give you some reflection information on your push constants, so you could technically automate the syncing, but I haven't done that yet in my side of things. This is dispatch indirect. We're not doing indirect yet. So to dispatch across the full screen, we need to do the div roundup. One of these boys. And voila, so we get the display height. It's fixed right now. We've basically got everything and we just need to replace these variables, but I've not bothered doing it. It resizes just fine. Just the rendering code is not rendering different sizes. Then we just need to make sure we do this one instead. And off you go. Yeah, it's crazy. Yeah, I don't know why people do that. Right. So we're launching a new shader, guys, which means that things could blow up and the stream could die because we're using bind lists and AMD drivers. Sometimes if you index outside of a descriptor set, could crash. If you have an infinite loop, it could also bring down the stream and computer. So we're going to launch it, and if the stream dies, it's just because of that. And I'll literally be right back. So let's see what happens. Right, we've got a black screen. That's better than but what we can tell is sphere ray tracer is going, right? So it's running across the full screen, and it's actually running at 0.04 ms, which is the exact same time it costs to actually clear the screen using a compute shader. Right, so effectively the ray tracing is free, if not quicker actually in this case for some reason. That's something to take note. This is like the baseline shader, this clear screen. I don't actually need a clear screen, I don't think, but I keep it there as a sort of a baseline of how slow is this to simply just mem setting memory, right? So this is what we will be comparing it against and some other things too. So first of all, we're not checking if we're outside the bounds and discarding, right? That's something we definitely need. So we definitely are going out of bounds with the memory writes, which could have caused me big problems. So we're going to start off there, right? We should just be seeing something big and red on the screen. Oh, it's not far enough back. That's the problem. It's 0, 0, 0, isn't it? So positive Z. So we should say, let's say it's 1,000 off into the distance. Pixel chord output dims was pixel chord. Right, so we'll have chord. Let's say pixel chord. Chord and E chord. Oh yeah. Doesn't write much. Right, yes, because it might not write to every pixel. Yeah, that's true actually. That's very true. But yeah. It is, yes, I'm writing. Right, so let's default the color to something just to check to make sure we can actually render to the screen, right? There's step one. So we're not going to do white, right? Because if not, we'll blind all of our faces. And I want to make sure we all have eyeballs by the end of the stream. So then we're just going to say, right, so we can actually write pixels to the screen. It's exactly the same time as the other one takes, which is interesting. Okay. So we know that works. So we never get hit back. So I put myself... Oh, the ray direction... Okay, so let's go... Let's make this negative 1,000 and see what happens. Right, it still doesn't work. Right, so we could go back to that code and compare it. Oh, we didn't return success equal true, did we? Oh, my days. Thank you so much. Look, mom, no hands. We. Thank you. Appreciate it. It works. Ray tracing. Ray tracing. There we go. So that's amazing. So we've got 1,000 here. 256. So should we put a bunch of these? So let's just say this thing is 20. What does it look at 1,000? Right. So let's just put a bunch of these up on the screen, and then we'll so we'll put them across the x-axis, and I guess we'll do like a little bit of a grid. I don't know. We'll just put them down, right? Does that still compile? Right. Good. So we'll go. Okay, this one is let's say negative 100. That's not good, is it? Negative 500. Right, there's two of them. So negative 500 is too much. Let's say negative 50. Right, okay, so 500 was too much. Let's say 250. Right, so that's at the edge. I'm hoping to see different field of view. I'm hoping to see it not be a perfect circle. Should we use the normal to color it? So we'll literally just get the hit normal and just color it, right? So yeah. So we just say basically so we'll say f30 times 4 hit.normal.x .y. So yeah, the normal is obviously just the vector, a normalized vector from the yeah, normalized vector from the what's what to say, from the surface that you hit, right? So if you hit here, so if your ray goes and goes boom, the normal is that, right? It's just a normal vector from the surface. So there's another normal, there's another normal. Right, so so that's obviously goes negative 1 to 1. So what we need to do is say times 0.5 plus 0.5, and that'll convert it from negative 1 to 1 into 0 to 1. So from signed norm to unsigned norm. Voila. So here's some things. See, I'm hoping to see it, like, should we up the field of view? So if we up it to 90, 45 just might not be enough. Right, let's make the spheres a bit bigger. So let's say, oh, they're, I don't know, 80 in size now. And then let's move the distance to wait, let's move it to the left by, let's make it 300. I just remembered, sorry, I should have commented out this code. And then, do I want the conversion from sRGB to linear on that? Does it make it look nicer? Question. I guess it gives it more colors, less white. But yeah. So what else do we want to try and do? Let's move it to the left a little bit more. I want to try and see the field of view in action, right? We shouldn't be seeing a perfect circle. Like, maybe we need to move it up into the corner. And let's make sure the XYZ is correct. Right, that went down. So right, as you can tell, it's not a perfect circle anymore. It's got a bit of a shape. So we know the field of view stuff is obviously lying. Where is it? So we need to flip the Y. Where do we flip the Y? There. Whoops, wrong one. Flip the Y here. Perfect, there you go. Okay. Right, that's good. So I guess what we can do is we can... So I think what I want to try and do now is like, let's fill up 3 of them at the top, and let's just see if we can think about a way to do anti-aliasing. I'm not sure if it's possible, but I just want to have a bit of an experiment. Like, because we get the hit position, we also get the normal, right? So is there a way we could sort of blur it near the edges? Like, because if you have the vector, you know, you have vectors from the camera to there, so you can maybe not. Maybe you have to do multiple samples actually. But yeah. Right, I'm just gonna pop out what that says, get a drink. Hit point versus the distance from the edge. Hey there, Sherlock, how you doing? Yeah. Because yeah. Because we did it with a sign distance field, basically. It came for free when we did our 2D SDF renderer. We managed to get the anti-aliasing there. So if we can get anti-aliasing working for these, that would be pretty good. Cast 4 rays, yeah, cast 4 rays. Yeah, maybe. Yeah. Right, I'm just gonna get a drink, I'll be right back. Right, let's enjoy the tunes. Then we'll see if we can anti-alias, hopefully. Hey everyone, welcome. How's it going? Well, thank you, Nurse. Appreciate it. Appreciate the raid. How did the stream go? Yeah, it's popped to get a drink and all that. Welcome everybody. Working on Game Van Engine. We've got like we've essentially got a lot of the foundation down. We've got like keyboard input, gamepad, that sort of stuff. We've got custom UI rendering. We've got a UI thing as well. A custom immediate mode UI, if you're familiar with that. So yeah, we're currently just working on the 3D, the way we're going to do 3D rendering with compute shaders, basically. So yeah, if anyone has any questions about the project, feel free to ask away. So on top left is Messenger View. Why is that? I'm Pain. So we're going to try and work out is, can we anti-alias for effectively free, right? There's no free anything in computers, but effectively free. Because like when you do it with signed distance fields, which we're not, but we did a signed distance field renderer for 2D, very flexible SDF renderer, is really crazy. You have a distance from the edge, which means you could literally tell how many pixels, like it was a flat 2D plane, you could tell how far you was away from the pixel, like the edge of the pixel, so you could anti-alias it really easy. So with ray tracing, which is what this is, can we make that smooth? Can we get a distance of some kind? That's the thing. Yeah, that's it. I'm Pain. It's supposed to look that way. It's because it's a 3D perspective, right? 3D perspective, so it's going to be distorted. This is the way it works. If you had a field, if you have an orthographic view, it will be a perfect circle. But because everything gets the perspective around the edge, you know. What is the project? It's a Game Van Engine, that's the project. We're going to get to the game bit later, but we're going to do some rendering tech stuff. So I think we should really actually get down in a like we should kind of figure out like what questions we're answering from this. I think we want to have a lighting solution. We want to know basically, can we render tons of spheres fast? And we want to probably be able to start maybe being able to model some of them. I'm not sure about the modeling. We could probably skip that bit. But we can at least have like, maybe we'll have a hard-coded model. And we'll just want to test and make sure we can have tons of them and it looks good. Yeah, I do have a VOD channel. That is correct. Thank you for the reminder. Yeah, if anyone wants to have a catch up with anything that I've mentioned, you can literally go back and watch the VODs. I do have a YouTube channel. I'm working on a video for which basically goes over the signed distance field rendering in 2D. You know, a flexible 2D renderer. And that will go up soon. I've got most of the slides done. It's nearly finished, and then I got to record it. So how could we anti-alias this? That is the question. Should make them a little bit bigger. All right. Maybe we could have been a bit bigger, but how can we do the AA? AA, don't solve the point on the circle, solve for the closest point. Use some trig to get the equivalent distance on the near plane. That is less than 1 blend is closest point's color to the final result. Come up with it now. Canva now completely absolutely works. Yeah, see what I was thinking you could do. 1 pixel. Right, what I was thinking you can do. I'm not sure if this is correct either. But you launch your your ray, and if it's near the, you have this ray here, right? You hit there. right? Your normal is that, right? So you can use the dot product to tell how close am I to the edge, basically, based on your direction, right? And then basically you want to probably just make it, then you could probably make it transparent based on how much that normal is perpendicular. I don't know. Right, but it could be some interesting effect. And then you would basically accumulate the color and that you know, and then that is it. But then again, you have to, if you did it that way, you have to step in order. You have to have your spheres sorted it in order. That's the only problem with that solution, which is possible. Hey, Membrillo. Hi, Center is on was how did you implement for drawing the spheres? Oh, we're just doing a ray tracing. In the compute shader. That's all we're doing. It will be on the VOD channel after today's stream. But we basically copied this C++ code. We un-C++ it because C++. What else did we do? I can't even click on the... Yeah, so we un-C++ this code. And then we just did a ray tracer in compute shader. So we just launched it across the compute shader across the whole screen. And we're just currently going over all the spheres that are hard-coded. And that's what we're doing right now. So we're just looping over all the spheres and then just doing a ray versus sphere thing. And if it's a hit, we get the color. We was going to get the color of the sphere, but we're just using the normal now just as a test. And then we just store that out into the texture. Very basic right now. This is not going to be anything close to what the final thing is, but we're trying to... Yeah, I want to sort the anti-aliasing problem right away if I can. And then we're going to test how many of these can we render using ray tracing. And then if ray tracing isn't fast enough, we'll probably try a different method, basically. We'll see. Right. Glorious Sir. We can do 2 rays, one to the original sphere, and another to sphere with radius +1. Ooh. If we hit original, then pixel is solid. If we do not hit the original, we hit the one bigger, then determine the pixel power. Yeah, yours is the same thing as mine. I see what you're saying. That's the probably more precise way of doing it. But your radius +1 is not going to be +1 pixel because it's in 3D, right? So it's difficult. You have to get the pixel, how big the pixel is at that point in space. It might be quite difficult to do that. How about we just roll a joint and think about this for a sec? Exactly. Yeah. 2 tokes, and then your brain will be so fried you won't be able to think about it anymore. And then you'll go into pure like muscle memory mode and just hope for the best. Yeah, it sounds reasonable. Your way shrinks, my way expands. Right. For sphere, it doesn't need sorting, right? I need to re-understand your way. Pro join arrays in 10D, exactly. Right. So Cranston said, let's finish off the Coke. So Cranson was saying, don't solve for point on the circle, solve for closest point using some trig to get the equivalent distance on the near plane. Let's draw it. So here's obviously where the eye goes, right? This is the eye. And then you got your sphere in the world. Bum 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 bum. Got your near plane, something like that. So it's really Shikol here. We haven't really got that in yet, but anyway. Wait, is that right? Yeah, there's your near plane. Good. So basically you're launching your array. So that's where the pixel is, right? Okay. So what he is saying, don't solve for point on the circle, so that's point on the circle. Solve for closest point. Right, closest point. Use some trig to get the equivalent distance on the near plane. Right, so the original ray grazes the sphere, picks up the same color. Wait. So now you're saying ray grazes the sphere, picks up some color, keeps going. Yep. The interesting case in my way is when we just miss. So wait, so what you're saying with your way? Like I don't understand. I'm not sure if I fully understand your way. I'm just going to try and decode it some more. Use some trig to get the equivalent distance on the near plane. Right, so then you would move to the pixel to use the normal to as not Cerebral was saying, use the normal to recast it to the left, right? Because we know it's gone to the left, right? Recast the ray again to the left-hand side. Do the same distance. Is that right? Use some trig to get the equivalent distance on the near plane. If it's less than 1 pixel, the closest point's color, blend it into the final result. Yeah, I'm not sure. You'd still have to... No recasting. Oh, okay. Draw a ray that just misses. Yes, sir. Ah, shoot. Right, we did it. Next one. We're trying to do some anti-aliasing and get it for practically free IMCAT pane. So we're just trying to figure out, like, is there a way we can get it to work? So you saying you want to find this point here, right? And that's what you want to find. So you want to do that, right? Is that supposed to be saying? Right, I think I know what you're saying. Right, then you want to get the distance, reproject it onto here or something, and figure out if it's a pixel. Gotcha. Right, so the question is then, right, here's the question. If it is a pixel off, right, meaning you need to AA and do the blending or whatever it is, what do you do, right? Do you keep going with say if I'm 50%, I need 50% blending. You need to keep going, right? This is the bit I'm trying to understand. Is that right? Yeah, you could use the sky color, but then that wouldn't be correct. You could get opposite colors, and the sphere behind you could be opposite to the sky or whatever, and it would just look wrong. So the original ray grazes the sphere, picks up some color, and keeps going. Oh, okay. So I was saying that I thought you said that you don't need sorting. But you need to sort that, right? In the ray. Oh, right. Color so far. No, but it's not blending. You need to blend it. Because that's the whole point of anti-aliasing, right? It blends. Right? Trace in the same direction from... No, you just trace in the same direction from the closest point. Yeah, so you trace in the same direction and you hit this guy, right? What do you do to the coloring, right? Because obviously, say this is just grazes it, but it should pick up a bit of the color, right? And then it needs to sort of mix it with this one, right? You can't just select this one. If not, what's the point of doing the graze check? You know what I mean? That's the bit I don't quite understand. So we could say, oh, we've grazed this one, right? So I guess you go, you find the closest one that you've grazed, because you surely wouldn't do multiple grazing. Yeah, so you're probably going to have multiple AA, or multiple grazes, right, in a row. So you basically store the closest graze, and then you store the one that you hit, and then you just merge the colors, right? That's all you do. That should be practically free. So you can still have a min. You can still not sort it and just min the values after all the checks. Got it. Got it. That'll work. We got this. So your way is probably more correct. My way was probably going to be off by, like, you wouldn't get the pixel correct. Ooh, what is this? I'm kept paying. Don't waste your time too long. I'm about to show you. If it's garbage, then it's garbage. Right, closest point on circles. You've got the point, center, radius. Where's your ray though? Do we need to work out the closest point? Is it? So in a ray verse. Yeah. You need this. Yeah, we need this. We need this. And then you get the distance from P. Right, so you need to figure out... You need to find P, though. I'll keep this around. I'm not sure if we need this exactly. We need to find something else, I think. So... Yeah, so we need this. We need to say... We need to find this point here. So you need to do something like... You probably get that vector. Right. Then you need to work out... that basically. You reproject it across here and get that point. Yeah, that's easy. Right, we got this. We got it. Let's go. Wait. Okay, so what exactly do we need to do? So I think we need this point. So we need to work out the distance from the sphere. And the way we do that is we need to work out the closest point on the ray. So to work out the closest point on the ray, you basically do this vector, you reproject it across the ray direction. That gets you the point. No, it doesn't. Let's figure it out. It would be helpful if things were... Okay, so you've got this vector here. So if you reproject this across there, 90 degrees, bam. That's right, isn't it? Yeah. So you reproject it across there, you'll get your point here. We can get that point. With this point, we can then determine the distance, right? So then we do this point, take this point, and then we length it, right? That will get us a distance, and then we can do the radius take the distance, right? Then we reproject that distance from that, like, it's in perspective. You've got to do some maths, right? This is the bit where I've got to learn some maths. But you've got your near plane here. You've got to reproject that distance across here. And if it's a pixel, then you do some AA, right? Oh, there's another triangle, guys. Triangles, they're everywhere. So that's what we've got to do. Right. So the first bit's easy, right? Let's get the point. So we want to do a... Right, so if we don't hit... So only do if we miss. So we've missed. We now get a distance to the sphere. So we've already kind of done that. So, you know, the optimizer should be able to work this out, right? Sphere to ray origin, but we want really ray to sphere origin. So did that even do anything? The dot of that and that. Right, when you square it... See, I don't know why they did that. Because they negated it. But when you square it, it gets rid of the negate anyway, right? It like absolutes it. And then these are... So really, you could have just done it as ray origin to sphere, which is the one we need. I think that's right. We will test it out, obviously. So it'll be that, take that instead. Then you won't have to do the negates. Not that it's probably that much of a big difference, but... Right, let's try that out. Shoot. Right, it still works. So now hopefully the optimizer should reproduce this. So you got that vector going from the ray origin to the sphere, right? You reproject that across the ray direction. So you do closest point on ray, which would be the dot product of this and ray direction, right? then you need to multiply that. Multiply S ray direction with the dot product of that. So that reprojects this vector. Oh, this vector here gets reprojected across there with the dot product. Then we multiply it by the direction to actually get this point here, right? So then, now we need to get this difference. So now you get your right. Do we need it in squared? Should we work in squared space? Yeah, we'll work in squared space, I think. Projecting the sphere circle onto any works if it doesn't hit. Yeah, so we haven't hit here, right? Oh no, oh wait, I see what you're saying. Yeah, because this could be T min, T max. That could be true also, isn't it? So what you're saying is you want this. So we want to say did. Right, if did not hit. So we'll set hit dot. So we did hit it, which is out of T min, T max. Right, thank you for that. Obviously, we can make this better later. We just want to make sure we can do anti-aliasing. That's the primary objective. Else if did hit. Hit dot did. Hit dot didn't. Right. Rightio. So you got this guy. So you reproject it. There's your point. You then want to do a difference. See, we're working in squared space. I don't think subtraction works, does it? Let's try it out. What's the thing on a test? Say we've got a distance of 50. Well, 50 times 50 is 2000, right? And the radius is wait, which one does it matter? No, it doesn't. So the radius is let's say 30. Right, 900. So it's that take away 900. And if you square root that, does that get you the difference between 50 and 30? To 20. Does that get you 20? That's the question. Where's the square root? I need my science mode. Science is... Where's this? Am I blind? Where's the square root? What? It's got all this stuff. Where's the square root? What's the power of 0.5? Is that really square root? I'll go for a bit faster, I think. My toy, if you're interested. Sweet, thank you so much for that, Ransom. Appreciate it. I'll take a look into that. Thank you, sir. So 1,600 to the power of 0.5. 40. It's kind of doubled, isn't it? We was expecting 20. So maybe it needs to divide by 2 after that. Yep. Should we try that again? Right, one more time we're trying this out. So let's say we've got 150. Square that. So there's that number. So then we want to say 100. Or maybe let's do 90 to make it a little bit odd. So the difference between 150 and 90 is 60, right? So 8,100. So this take 8,100 is this number. Then to the power of 0.5, 120. Difference is 60. Right, we've got the formula. So if we want to convert from squared space back into if you do a subtraction, you need to make sure you divide the result by 2. Right, so remember that just in case. Yeah, I'm not sure though. We'll see. But let's take a look at this thing here. What is this? Oh my days, more CPP. There's a faster one, interesting. But does it get you the... Right, then you can work out the rest. Let's take a look at it. Let's see how it compares. Right. So that'd be F32 times 3. That'll be 3 F32. Right, so where's it faster? So it's in the sub. The dot product between these two, that's there. That's the length squared operation. That's the squared operation. Then it's doing the... Then the minus. This is all the same. Oh. No, it's not. There's some that is then made redundant. Interesting. So maybe I have to make this redundant. Right, let's take a look into that. Then there's no square root. Wow, and none of that. That's pretty good. Right, should we apply that then? So simply he's doing, so radius time, to work out discriminant. Radius times radius plus the dot product, the length squared of midpoint. Where's midpoint? Ray direction dot, yeah, this one. So what midpoint? Plus midpoint length squared. So that's still float, that's good. Minus this length squared of this. Right? So apparently we should be able to get rid of this. And then the distance is midpoint, so sub, right, you still need the square root, But we don't have to work out these two and do a min. So that's definitely faster. Square root f32. Okay. So that's your so we'll call that t. So then we need the t max check. Yeah, that's definitely better, isn't it? Well, hopefully it works. So we'll just oh, whoops, what did I do there? What did I do wrong? Yeah, it's not. I thought I did. Oh, whoops. Thank you very much. Wait a minute. Oh no, sorry, I had it. Right, what did I do? Oh, I see now. Right, gotcha. It is, isn't it? So it's one of them. Right. That's much better algorithm actually, isn't it? That's pretty cool. Still works. Amazing. Sweet, thank you for that. That'll make it way better per pixel then. Sweet. Would you look at that? Oh yeah. Beautiful. Right, maths time. So now I've got this closest point. Right, so got this guy. Right? Let's go back to here. We've got this point. We now need to get the distance. We need to get this, the distance between here. So we get the distance between there. We'll work at it we'll square it, and we'll see if we can avoid doing we'll square root it, and we'll see if we can avoid the square root later. So on the distance between, we want to subtract. So go toward. It doesn't really matter, actually, the way. Sphere center position. Right, and then we do we probably just want to do a length of that. Distance to the center, take radius. Yep, exactly. But I'm hoping we could not do the square root in there. Yep. So, ooh. Yeah, so we're saying distance from edge. Right. Yep. Gotcha. So now we've got this. We need to remap that into here, right? How do we do that? So all the near plane where the pixels sit, we need to remap this distance and should it just be divided by z? Like, think about this. If the near plane's at 1, then it might be you can just divide by z, right? And then you check if that's a pixel. Should we try that and just see if that'll work? So we want to work in screen space. So the distance. So where's the distance? From pixel point, draw a line to the view boundary. Yeah, then take the distance. Yeah, I think you can just divide by z though. But that's another way to do it, Glorious Sir. And if this way fails, I'll try that. So I think we just need to say divide by, so we get z, so depth. Depth length. So divide by depth. Right, so what we want to say is, if it's a pixel, let's just set the color to something really ugly like a blue. Right, and then we'll make sure it's always red. Yeah, we'll bring back the red color and we'll set it to blue. So we'll say if the distance from edge in screen space is less than a pixel, we'll say, hey, the color, by the way, and then we'll say found hit equal true. We'll say, hey, by the way, the color is blue. So we'll just do like times 4, 0 red, 0 green, 1, 1. Okay, and we got the... What? Whoops. S.radius. Radio. Fingers crossed. I can't believe we haven't got a GPU crash today. This is groundbreaking. Right, so everything is blue. Everything is blue. No. Let's do greater than and see what happens. So we don't get a blue there. Right, okay, something's clearly wrong. Obviously. So we did not hit. A red ball? Yeah, it's been more than just a red ball, but yeah, went back to red. Hey there, Pi, how's it going? Good to see you, how you been? But yeah, we're gonna try and make the whole game out of spheres. So we're just trying to see how fast we can make a ray tracer, because this is gonna think it's gonna give us the most graphical fidelity. But there's also a super fast way to render stuff using compute shaders, which we'll do afterwards. I'm just trying to make sure that we can solve the A problem for maybe close to free, the hope is. But yeah. How's things going? So divide by depth is maybe not correct. I don't know, man. I don't know. Right. Will you also be doing 3D models? Yeah, we're gonna basically do a 3D model. Well, we'll make an application or an editor, but we'll just be able to like model our own custom it, because it's all made out of spheres. It will support like boned animation and stuff. But we'll just go watch out for whether there be holes between the spheres that sort of get separated. So the spheres will stay in a sphere shape. It's just the positions will be blended across the bones. And so we should be able to just do all of that in a custom editor. It shouldn't be too bad. Yeah, we just got to try and put as many spheres on the screen as possible and see how good our graphical fidelity could be. So like Blender, well not really, Blender's quite difficult to use. This will be a lot easier. This will literally just be like I'm just painting spheres down on a grid. And we'll do some special stuff so it doesn't look. We'll do some special stuff so they place nice than just being on a grid. But effectively they'll be on a grid. We might be able to do different sizes and just paint it down. It'd be more artistic, right? As opposed to technical. Going decent, still in the moving process, so not much free time. Oh, cool. Where about you moving? Are you just going down the road or are you really changing location? Have you upsized as well? How's it going, Ray March? Welcome, welcome. Good to see you. So if we've got a depth, so we've got distance to here basically, which is then the same distance to here. That's what we really want. Wait, what do we want? Yeah, we're looking at the distance to right. So your near plane, right? Maths. There's our Z. Wait, sorry. No, sorry. X, Y, X, Y, Z, and that's the right. So that's the ray direction. Is this with a near plane? Right, so as you increase the field of view, I'm just trying to figure out how this thing works. As you increase the field of view, the near plane will probably stay the same. Definitely upsize. Sweet. About an hour away with buying with that house. Oh, you remember you saying. Sweet. You get to tell your children about all the things you used to do in that house. You know, just yeah, I have no idea how badly I'm looking forward to having my own office. Sweet. Yeah, own office is good. I actually take it for granted, not gonna lie. But yeah, pretty decent. It used to just be in my room when I was living around my parents' place. So I just did work in my room. I didn't mind that, but obviously it's not in your room when you're sharing your room with someone else, is it? Um, yeah, that would have been different. So, right. So the near plane, where is near going to sit? So if near sits at 1. Right, so you can get that distance. So if you did 1 across all of the ray directions, it would be like curved, wouldn't it? Right, if you did it across every pixel, it would be kind of curved. Hmm. Right, let's Google for it. I've done trying to figure this out. So we're trying to work out how do we map a to the near plane. How do we map a pixel? How do we map a? We want to map like a vector to the near plane. What is in near plane? I thought it was just a divide, but I'm a bit wrong. Need to do some trig. Good old trig. Yeah, I think you need to work out that, isn't it? Like that. I just don't know how you do it. I could probably work out if I tried. Like you have, you have this distance, and you have that distance. We actually have them all, right? We're trying to work out like a length of 1, isn't it, or something? Well, it's whatever the far field of view is that many degrees, and you basically just need that going across there. What's the length there? You know, and you get that triangle. Something like that. Something going on there. I'm just spewing maths, but oh, you gotta go. Ah, no way. That's cool, Clarissa. Thank you for. I'll check the link. Appreciate it. Mapping in the 3D to the near plane is more or less the traditional projection matrix, but you just fix z to 0. Huh. Yeah. Fixing the resulting z to 0, right. Hmm. Is that Buckhead? Maybe. Do we land on Buckethead? No, it's Stone Rebel. Stone Rebel, man. Still Stone Rebel. Not sure what this means. Not gonna lie. Right, so we're trying to map, right, I thought tan would come into it. Because, oh, I've just realized. The distance from here to here is tan field of view, isn't it? Something like that? Times 0.5. Yeah, that's it. So the distance from there to there is tan 0.5 times field of view in radians. Right, so let's get that in there and maybe we can work out the rest. Sweet, Clarissa. So, and let's just call this V. So it's like tan 0.5 times radians. We convert radians field of view. So that's where you're near. That's the distance to your near plane. At least. The rectangle, so this guy's trying to work out something different, right? Depends on the field of view and the far clip distance. Section near clip. So do you divide by the near? So I'm not sure. So I was trying to work out something different. See, I've seen this before in like a triangle rasterizer where you sort of reproject it back into the near clip, isn't it? So I've seen that in the past. Pixel position at the far clip plane, actual triangle surface position. View ray direction. So, should we just look at the code for like a triangle rasterizer, basically? Because that's the maths, isn't it? I'm looking for. Because they basically map where they do the mapping. Where is it? It's not it. That's actually just rasterizing it. This is the same page we did. Right, something like this. It's like a bit. Right. Near clip plane, 0.1. So ours is probably something different. It's like whatever that field of view. With the field of view thing we had, right? So near clip plane times camera x camera. We convert to screen space. So that's a camera position divided by negative z. Right, so with this value here, that's a position though, isn't it? We don't want to translate a point. Right, let's try it. This times divided by, let's see if that'll work. Right, it shouldn't all be blue. We shouldn't have a blue outline. So they did do negative depth, but I'm not sure why. Doesn't seem to make any sense to me. It says our depth. So we just did it without the mapping it to the screen. What do we get? Okay, so we get an outline. This is kind of what we're looking for, right? We're looking for something like this, but it's a bit too... Well, it actually looks perfect. Except for here, maybe getting 2 pixels. But yeah, let's go over to this one. This is not what we're looking for. It's a little bit off. Because that's the distance in world space, and it's not kind of... Wait a minute. Yeah. So the interesting thing I want to see is like what is... So can we print this value out? So we can say if dispatch, wait, ucoord.x equals 0 and ucoord.y equals 0, we can do GPU hprintf v equal f. So we only want to make sure that one thread of the compute shader actually prints out, right? Because if not, it'll just spam out too much information per thread. So what a value of 1? So we did 9, so we changed it from 90 to 45, which it was before, or is it something different? Okay. That's interesting. So with 90, so it is at 1. Okay. Good to know what that value is. So our near clip plane is at 1. So what sort of depth are we getting around the edge? Should we get that print code back, actually? We'll just print it out. So we get a bunch of depths, basically. Depth. Wait, distance from this one. So distance from edge is all of these values. Yeah, it's not good, is it? Let's do... let's see what the depth is, basically. But the depth is at like 1,000 odd or whatever. So we've got the distance from here to here, right? And we need to work out if... So, sorry, we've got the distance from here to here, this thing. Then we need to work out, like, what is its distance across here? So I thought if we divided it, brought it back to here. So... But yeah, you need to take that field of view into account, isn't it? Hmm. Hmm. Um, so we've got the distance from there to there basically, and that's 1. But that's what V is. So this is just too much drawing over the same thing. Let's get rid of a lot of that. So we've got the distance from here to here. That's what V is. Right. So we're kind of trying to snap that sort of like thing there. How do we... Right. So we've got this thing. We've also got the distance from there to there. We've got this vector here. Right. You had a vector from there to there. So camera origin to... Wait. Yeah, so to map this point here down to here, this might be the easiest way to do it that I can think of. We just need to say... So we've got the distance from there to there. So it's simply that distance, take that distance, gets us here, this point here, effectively. There's definitely a better way to do it. And then we can do probably this vector was that point. Take the difference. Yeah, I think we'll roll with this way first, get it working, and then see if I can think of a better way to do it. So the way that I'm thinking about doing it is you've got this vector here, right? So you've got this vector here, your distance of, so there's your sort of near plane distance. So it's that sort of like closest point, that's just ray direction, right? So you want to say like near plane at ray at near plane, which would then simply just be multiplied ray direction multiplied by near plane distance, right? So we can do that. So that gets you this point here. We now need the point from where, so really you just need the hit. So, so there's a little bit more extra maths. Yeah, so we got the distance between these guys. So you do that, take that, then plus the radius, normalize it, then times the radius, get that point. Yeah, it's definitely not the best way to do it, but let's just try it. Right, then you norm it. Let's try it. Closest point on sphere. So it's normalize it, multiply. And then I'm adding that to this. Horrible to read, but let's just get it working. Okay. Closest point on the sphere. So you get the vector towards that, and then projects onto the near plane. So you want to say like at near plane, right? Something like that. So it would be normalize it. So it's basically this normalized. Well, let's. Oh wait, why did I get rid of that? Wrong one is this one equals one sphere and done. Right. So then you take the difference between those two and then check if that's less than. In screen space, len f32 times 2 or times 3 or something. If that is less than 1, then color it blue. Multiply. That's right, no? Oh, shoot. I didn't make that a vector, did I? Alright, we're good. That looks pretty cool, doesn't it? Nevertheless, it's wrong. It's not what we're looking for. Like, why is it very bitty? Like, what's going on? So is something wrong with my closest point on sphere? Plus, so you subtract closest point on ray to yeah, it's terrible, doesn't it? Now it'd be fine running it again. It's very weird though. Very weird. What does it do greater then? Obviously it does the opposite. Ah. Right, so you got the sphere position plus this sort of we're trying to, this vector, we're trying to just get that vector there basically to the edge, right? So we're just adding that. So its closest point on ray. Maybe some of the original stuff is wrong? Ray origin to sphere, perfect. The dot product. Right, so it's not normalized, that's fine. Dot product, then you multiply the result across there again. That gets you the closest point on the ray, right? Closest point on ray, take away the sphere. That gets you a vector towards the closest point on the ray. Oh, I normalized it. What is that? Why am I doing that? No, it's fine. And then you're multiplying it by the radius, which is fine. Then you're adding that to there, so that's the closest point on the sphere. Perfect. Right. You need a subtraction from the ray origin. That's the problem. Towards there, did it compile? Towards here from the ray origin. Oh, we didn't subtraction, did we? Damn it. Right, so you just subtract length squared. And voila. So this is clearly not the most optimized way of doing it. There's a better way, which we'll find out. But we just want to make sure the anti-aliasing is possible. Ugh. We're in the same sort of problem, aren't we? Where the whole screen is blue. Like we're doing the distance across the near plane. I am confused. So it did it the other way, wouldn't do anything? So the blue is here. For some reason. Wait, it's curved, isn't it? It's going to produce you a curve, isn't it? That's the distance from there to there, but if you do it across vectors, it gives you a curve, like an eye still, damn it. How do you avoid that sort of eye? Yeah, so the problem is you're not getting it in. Like, you're getting. This is flat. But when you have a vector going that way and a vector going that way, and you know, you've got the distance between from there to there when it's going completely straight. But if you got it'll produce like a curve basically based on the field of view. That's our problem. No, we're not doing ray marching. We're doing ray tracing at the moment. We're just trying to see if we can get kind of free anti-aliasing. But I just tried to do it a different way, a more expensive way, just to see if it'll work. But or if I could get it to work quicker. But it turns out we just did it wrong again. Also. So yeah, just trying to figure out the maths is all. So let's undo that part we've just done and get back to the more simple code and see if we could get that to work. Right. I might take a quick tea break. I'm gonna get another tea. And then we'll come back and we'll see if we can get the answer. You want to use compute without any hardware specific accelerators? Yeah, basically. So just full compute. So we're just trying to produce an edge boundary here. The blue should be the edge boundary, but it's currently covering the whole screen. So we're trying to get some anti-aliasing for free, but it's yeah, just it's not working. That ain't gonna help, is it? No, 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 of course it's not, because of the if statement. Just making sure that code was right. So if it's here, it didn't hit at all. Here it did hit. Good. So if it did not hit, then we can do this. Right. Exciting stuff after 30 days of GUI. Hey, it went 30. Was it 30 days of GUI? Maybe it was. Was it? I don't think so. But yeah, we did a custom renderer, isn't it? That was pretty cool. But yeah, exciting stuff 3D. Right, I'm just going to get tea quick, and then we'll tackle this problem. We got this. All right, BRB. Right, welcome back everybody. So I think I figured out where I was going wrong with that previous way. We was trying to remap it. We was trying to use like a normalized vector, which was really dumb. I think we could have supplied the divide thing and then land the point back there. And then we can just measure the distance between the 2 points. I think we can do that. So we've got this point here already. Let's re-get this point that we just had. Can we redo? No, we can't. Okay, that's fine. We can do that. So we recalculate that, which was... so I'm going to go from a sphere to closest point. Closest point on sphere. So which would be closest point on ray. Oh yeah. Normalize. Normalize that. And it's a multiply. Right, does that still compile? Right, because it's times 3 instead, that compiles. Good. So what we need to do is we can then bring those closest point on spheres and rays back onto the clip plane. The near clip plane, I think. So this is near clip plane distance. So that's distance from camera. So apparently to map, so this is just 1, so it's not really doing anything. But we should be able to bring this onto the screen, right? So we'll do in 2D, right? Screen space. So that is literally just closest point on ray, right? Dot x divided by, it's kind of divided by depth, but because this is times by 1, but the field of view could be actually changed. Like our field of view is 90, so it's actually got a distance of 1, but it's not, but that's configurable, so we've got to do that. And then you do your sphere. Shoot, that's wrong. Sorry, I went too fast. Kind of did that wrong. Dot x, right, then it's this. Dot y, okay. Repeat that, replace the word ray with sphere. Good. So now we just have to work out the distance between those. So it's now just the length f32 times 2 between these two guys. And then that will be a length. Oh, what we're doing down there. That'll be a length distance from edge in screen space. So hopefully that's it, and we can get the anti-aliasing working. Fingers crossed. Closest point. What are we doing? I moved it, didn't I? Length operation between these. Oh, we're meant to do a subtract. Whoopsie. All right. Redefinition of right. Here we go. Does this work? No. Why? Why is it? But then if we did greater than, right? Okay. So what we're hoping to see is a border around the edge of blue. So are we getting a really big negative number, right? So we do printf. So let's do else for a minute. Yeah. So if we did GPU hprintf, we'll say this, right? So if this shows a value, then what that means is, that the calculation is wrong. If it doesn't show a value, then it means all of the, okay, because this code here is only running if the ray didn't hit the sphere at all. And what we're trying to check is like if you're a pixel out. So if it doesn't show anything, then it means the rest of them would have actually, you know, hit the sphere basically. The rest of the rays would have hit the sphere. Something like that. Or gone into here. Did you want to try out my fuzzy finder I wrote in C? You wrote fuzzy finder in C? Hey Tobeaver. Not really sure if I have the time now, but what was it fuzzy finder? Is it like grep? Right, so not seeing anything print. This is promising. This is promising. Oh, FSZ. Oh, cool. Yeah, it's like grep. Very cool. Good stuff. So this is quite promising. Now this means... Right, what does this mean exactly? So the rest of them are going into here or here. Right? So that means so if I put it into here now, it means the number just must be negative? No. I'm confused. Let's just point on Ray. Oh, did I do a length operation? Oh, maybe I'm supposed to say .z. Right. I think that might be the missing link. Alright, let's try that out. Right, so not seeing anything. Okay. Um... So let's do like 4 for some reason. Let's just try that, see what happens. So we did 4. We expect that to be 4 pixels out. Didn't seem to work, did it? Distance in screen space. That feels wrong still. X, Y, X, Y. Right, we didn't do the add. Shoot. On this guy. Add F32 times 3. So that was just a vector in the end. That closest point on sphere was wrong. Right, this closest point on sphere wasn't correct. It was just that vector. So we've got to add it to this position to get it to there. And then we're mapping these 2 points down to here. And then taking the distance between those. So hopefully that will be it. Right, let's just double check everything is correct. So ray origin to sphere, right? That's fine. Closest point on ray. The dot product between those two, perfect. Distance from edge, we haven't used that one yet. Closest point on sphere, add that. Multiply, normalize, going towards the one on ray. Yes. Yes. Multiply radius, perfect. Yep. That's good. So what are we seeing here? Are we seeing a lot of blue? Yeah, it's in a full screen of blue. Screen space. Less than a pixel. We shouldn't be seeing it for the whole screen. Something is weird. But yeah, I want to try and move this one here, this distance from edge thing, which should be the quickest way to do it. I want to see if there's, let's see if we could do it this way. Because I've got some new knowledge now. What happens if we divided it by closest or Z or whatever? Shoot. Right, so how do they map what they're doing here with this triangle rasterize that we're looking at? Screen call it, pin it all together. Which you can run steps. Convert a point into camera space to screen space, essentially projects the point onto the canvas. This is what we want, right? But keep in mind, they also need to store the original point Z coordinate. The point in screen space is, okay, three-dimensional, right? Three-dimensional. And the Z coordinate will be useful to solve the visibility later on. Right, they say negative Z. Negative Z. Is it because Z is negative? I don't understand that bit. It must be because their Z is negative, right? I know. Okay. So they're saying near, convert camera space. So wherever it is in the camera. Yeah. Relative from the camera. Times by the near. Right, which was field of view. Tan. Do they do that in this lesson? I don't know. They already use tan, to be honest. I didn't really use tan in here, so I'm not sure how they worked out the near. It's hard coded. Right, so they worked it out as near. Right, okay. We then convert the XY points into screen space, in screen space to normalized device coordinates. Right, we're not. That's easy. That's just divided by the width and height and all that. It's not. That's not the hard bit. So this seems correct. Rest, and then convert from rest to space. Times image width. We now project the triangle onto the canvas and convert these projected vertices to raster space. Both vertices in the triangle and the pixel live in the same coordinate system. Then it went into normalized device coordinates. And then went back out to the screen. Oh, wait, no. Top left, right, bottom. Oh, what sort of range are you going to get these in? Because then they're saying divide by, so that's the right, left, so that's width. So what I get is, why do they go in this example down to screen space and then go back out into some image thing? I thought screen space would just... Hmm. Right, let's take a look at another example and see if that makes more sense. No, it's not right. Yeah, we've got it open ray tracing on weekend. We just tried to do it to distill this sort of algorithm here, the Rayverse sphere. But turns out someone gave me an even better one, so we're not really using that one anymore. We are ray tracing spheres, that's the idea. We're just trying to anti-alias the sphere for, free. We're trying to get it, so we're just trying to get an outline around this sphere in blue, but obviously the whole screen is blue, so it's a little bit wrong. So I'm just trying to figure out the maths on how I'm trying to calculate a pixel away from the edge. Like if we miss by a pixel, basically. I'm just trying to work out that maths. And then the rest should be pretty easy. Right, I'm not really gonna understand this. So I know, for example, to look for, because I've written this before, right? Where you map, but I just, I'm forgetting the maths. When you will map, if you used to rasterize a triangle onto a screen, I just need that sort of maths, how you project it back onto the near plane. I need to work out how we do that. They've probably just written the rasterizer in it. Ah, damn you, Microsoft and your two-factor authentication. Yeah, this is what we want, right? This is got projection code. Okay, so let's just find where that is. It says it's simple. Let's find it. Why is every function in a separate file? I could just tell just looking at the names. Every function is in a separate file. Damn these people. Right, okay. So we're just trying to find the bit of code that sort of like maps the projection. Must be good enough. XZ context. Coefficient, I imagine that means. So that's probably the tan thing, right, which we had before. Depth equals Z plus camera Z. I guess so. I guess so. Yeah. So you can shoot multiple rays, but we're trying to do it without shooting multiple rays. That's the idea. Because if you shoot multiple rays, the problem is we might have to trace the ray across more. Yeah, we're trying to make it so we want to tell how much we missed by, and then use that. So it's kind of an optimization what we're trying to do. So your depth is there, ABS to depth. Sure that is. Coefficient Y divided by depth. This feels wrong. Where's Y in all of this here? Right. Yeah. Yep, that's what we were doing. Plus the camera. That's exactly what we're doing. Like it was right, is my Y coordinate off? But then the X coordinate should be fine. No, it's the same thing, they're using the same number. See, I don't know why they did a separate function. This just seems really weird to me. Why is the X and Y one? This is like banana. Right, oh, because they invert the Y. That's why. Right, let's keep looking. But okay, no. It feels like... Right, let's refactor this to make sure, and then let's just double check everything. Because to me, it just feels like... Got that right. Well, we're using the same maths. There's that thing, you know, there's the past two things have been telling us it's this maths, and that's what we've been using. So closest point on sphere, screen space, nuclear plane, distance, times this, which is, you know, it's 1 times this basically. Divided by the depth. Yep, that's fine. Same with these, x, y. Cool. Then we do a subtraction between these two and these two, do the length. Right, so this is fine. We know that is. Right, and do you want a length? Like, or do we want a max? I'm not sure. We'll look into that. We'll think about that. That's probably just a little small issue. Yeah. Okay. So closest point on ray is ray direction times the dot product of origin to sphere, right? With the ray direction. So how does that reproject over? That's fine. So that is, how does this vector remap across this vector, and then we apply it? How much does it remap? And then apply it. That's fine. This distance from edge thing is not really used at the moment. We want to use that in a bit. Let's comment it out. So then we're saying closest point on the sphere, closest point on the ray, take away this sphere center position. We normalize that. See, is when I've not used normalize yet. Have I used normalize yet? Is it a special function in the SPIV code base or in our compiler? Right, it's a special instruction. It's going to be right. So that's just the CPU implementation that we saw, but it's going to be right. Closest point on ray. That's a... No, it's direction. From ray origin. But ray origin is 0, 0 though. But still we didn't apply it. So for correctness when the camera moves, we need to do this. So that's for correctness when the camera moves. We haven't moved the camera though in any way. So from the center position to the ray, right, multiply the radius onto that. After you normalize it, add it from the center position, closest point on sphere. That makes sense. What can I do to debug this? See, the crazy thing is if we literally just do this, it kind of works, right? But it's not. So we can play around the values. What? Oh, okay. So we do this, we kind of get what we want, right? This is what we're looking for. Is looking for a bit of blue that goes around the edge. Bearing in mind, this is not 1 pixel because you can see there's a couple of pixels. So we could theoretically just do that, but I think when you shrink it enough or put it far enough away, it's not right. So if we was to put this 10,000 away, Can you see we're just getting a couple of blue pixels, and that's not right, is it? So there's something to transforming it to being on the screen. Let's remove this multiply and see if it's just something silly like that. Right, still don't work. Yeah, man, Stone Rebel, pretty sure. Yeah. So we're also doing 2 spheres. Should we just do the 1 sphere? It might be because of that. Right, let's focus on the 1 sphere first. Do a single sphere. Syntax may seem much sweeter where objects and subtypes play. Okay. Oh, the song, yes. No, this is GPU code. This is shader code. We've got our own custom compiler. C compiler to SpearV. So it just compiles shaders, C code, so we can share data structures, functions, and all this good stuff, basically. Yeah. So this is a compute shader. But yeah. That's the basic gist. Yes, this ain't doing crap. It's still just, let's put this back. Something else is fishy. Right, so if the field of view is 90, it's 90 degrees. Means distance is 1. So times x and y by 1. Right, I think that makes sense. So it's something must be wrong with these closest points. Ray direction is normalized. This is from ray origin to sphere. Right, bear in mind that is just 0. That's got, it's not a normalized vector, it's got some form of magnitude to it. So when you do the dot product between the two, it gives you how much it projects across the other one, right? And then you can apply it with a multiply, right? It's not wrong. Then you add it to the origin, and voila. So when you take the difference between the closest point on ray and this center position here, going towards the ray, we normalize it. Then we multiply the radius, multiply it with the radius, and then we add it from the Come on, this is just it. This is just it. So what is... What could possibly be wrong? So you turn into clip, you know, onto the near clip plane, like so. And then you get the distance from the edge by doing closest point on the ray, take away the closest point on the sphere, take a length of those. If that is less than 1, right, then color it blue and say we've hit. Right? And then so it should just be black for the rest of it. But they ends up being... Is it because the distance is so far? It can't be. It could be. It could be it, right? Thank you, Ramel. Appreciate it, sir. It could be some floating point inaccuracy, maybe. But will it? Divided by 1,000, isn't it? Because it's 1,000. Yeah, that feels wrong, doesn't it? X, Y. Should we move it? Let's move it closer and then drop it by 10. Yeah, drop the radius as well. Yeah, it feels wrong. Let's run the... Yeah, ends with a seg fault. Yep. It's a good video. So your Z is at 1,000. Right. I can feel like the maths is wrong now. So your X is a 0. Oh yeah, but 0 by 1,000. Right, or whatever, okay. Okay, so let's run it. So you've got like a ray that shoots right here. Or let's say a ray that shoots over here, right? A ray that shoots, and then like you're comparing it, you know, against the edge, the nearest edge here, so something over here. You reproject those back onto the near plane, and then you take the length. But when you reproject it, you're saying divide by 1,000. So they're going to get, you know, the one that's further away is going to get really close. Yeah, something feels off then. When you're dividing it by 1,000, it's going to get pretty close. So of course they're all going to fit next to each other and it's going to go blue, isn't it? Yeah, that's off. So how then do people... Do we need some... Is it going to bring you into... Right. Yeah, so this number's not going to be correct. It's not going to be on... It will bring you on the near clip plane. It gives you like an XY, right? But it's in like clip space. That's the problem. It's not in pixels, is it? That's the issue we're facing. Right. So when they did this with the triangle, they then convert it into normalized device coordinate and then turn it into the screen. Okay. Right, I think I know where we're going wrong now. So this left, right, top, bottom, they count. Well, I was thinking that was the screen. I was like, why are they doing that? And now I realize it might be the left, right, top, bottom of the sort of camera projection. I'm not sure though. L is what is L? The term LR is left, right, top, bottom coordinates of the canvas by rearranging the terms. Right. So what do they mean by canvas is the question in this example. Right. So by canvas, the first onto the canvas, then the restoration of the triangle itself. From screen space to raster space. Right, what problems are trying to solve? To project onto the canvas and then convert their coordinates from screen space to raster space. Pixels and triangles are then defined in the same space. Yeah. See, when the word screen was confusing. Yeah, the sort of virtual screen, and then map it onto sort of like the texture in pixel space, right? So they convert it into normalized. Right. Let's see where we're going wrong. So how did they get the left, right, top, bottom? Um. So it's bringing it to normalized device coordinates. How did they get the left, right, top, bottom? That's what I understand from this. They've already got RL and that here, and then turn to normalized device coordinates into raster. See, that bit's not hard, it's just what is this? Um. So if we divide by 1,000, then if x is at 1,000 to the left, it would be 1. So when this is like 400, should bring them both back. Have a bit of a play. Wait, no, let's not bother. Let's just move this to 1,000 to the left. So that's 1,000 back, 1,000 to the left. Shit, what's going on with all this? Oh, it's to the right, sorry. Anyways, regardless. So that's about 500. So the width of the screen is 1280. But yeah, you got the field of view of 90 or whatever, but right, so if we do 640, does it get wedged right in? Trying to think of the space we're in. It's not dead in this, you know. I'd just change the field of view and make it wider, wouldn't it? Yeah, I'm not sure how they work out the coordinates of the canvas. Because when we do the field of view calculation, let's just get that back to 0 again. We pass in the dimensions of the canvas anyway, right? And that'll calculate our ray for it. So we end up doing a division. So I'm trying to think about the number that we're getting. Right, so we're doing like 640, or whatever it was, right, divided by 1,000. Gets you, you know, something like 0.5. You get 0.5 along the x, and that's at the edge of the screen. So if you then multiply that by, like, so that's going to be relative from the middle. So you multiply that by the screen size, right? And then offset it by half the screen size. Then that's going to, well, you just need screen size. That's all we need, isn't it? Right, then multiply it by screen size. I think we're getting somewhere now. So multiply it by BC output dims.x. Right. Y and Y. I think that's going to be better. Right, we're not quite got it there. So that's interesting. Should we multiply it by half those dimensions and see what happens? Right, let's try that out. Because it'd be relative from the middle. Yeah, you want to scale by half the dimensions, I think. Because it's in signed norm space. Come on. Come on. So if we up this to 4, what happens? 4 pixels. Been away and going again, not sure if this is helpful. Intuitively, what we want is length view projection times closest on the line. So XY. Yeah, that's effectively what I've got written. I'm just trying to project it back onto the space correctly. But I've not got a matrix, so I'm just doing it manually. Yeah, that is exactly what I've got. Just doing this first, it might be good, then optimize later, removing the Z row. Yeah. Things I already got my matrices, that's one of the other ways. See, we're back projecting. Why? I noticed that the view projection is not invertible. Right. So we're projecting back to the... Yeah, we could just take a pixel and say, what is a pixel at that depth? Is that sensible? Hang on a minute. Let's redraw this. View. Near plane. Circle. Circle. Or sphere, whatever. Sphere. Ray. Just missed. Missed by a hair. We have the... Right. So you've got this point, that point, and you got that distance. That distance is not exactly this. It's a bit angled like that, right? Because it's distance from there, you know, it's like that to that. It's a little bit angled. For a given near plane point is not a 3D single point that corresponds to. They lie on the line. Right. Okay. Yeah, so you can't bring it back to here because, or the distance or whatever. Yeah, I'm not quite sure I get what you mean, but I think I understand a little bit. Back projecting back to here. Notice that the view projection is not invertible. Multiple things like that. Right, so multiple different points land onto the same pixel. Right. Okay. So we have like a pixel, we know the size of a pixel, but then what is a pixel at this depth? Right, so at this depth, how big is the pixel? If we just did that, that might be easier, right? And quicker. So we know, so a pixel so the near plane, my experience is that these things in scalars in your head is really hard. Better working with high-level constructs like coordinate space transforms, matrix modifications, projections of points on lines and given formula that look up, etc. Right. Right, convert between spaces, fair play. Yeah. I don't have the matrices at hand though. I have to build a matrix thing at some point. Because I have a 2D matrix that I built for the UI, it's got to build one for the 3D. Because I wanted to, do a 4x3 with an implicit 4x4 row. But we'll be doing that in the next stream, I reckon. Or maybe next couple of streams. So, size of a pixel at unit length. Or at, So depending where the near plane is, so it's one. Yeah, so that's the size or near plane distance. So it's that times the depth. Right, let's try this out. As always, you can build a matrix in SymPy. Strip out scalar equation. Yes? Yeah, that was a good tool actually. That was a pretty impressive tool. Probably be using that some more. Very soon. So I want to work out like how big is a pixel at depth. Pixel at depth. So it's near clip plane. So where are we looking at? At closest point on sphere? Which one do we want? Closest point on ray. So that's the depth. So we do origin to closest point on at origin to sphere probably. Times this dot that. Oh, same plus file on server, sweet. Yeah, I think you sent it to me before. I'm not sure. But yeah. It's all three of the albums, Indigo 1, 2, 3. Is it Indigo? Is that right? Yeah. But that's some more, sweet. Have you got the link to that server, by the way? I kind of lost it. Right. So pixel at depth. This is another way of doing it. So then you just get the distance between these two things. And then you check if it's the times that. If this, so then you don't have to bring it back, there's no division. Right, just multiplication. Right? That's interesting. So we just need this. That one. Damn it. Right, let's see what else we can achieve. Let's times this by 2. Right, we're not seeing it. What is this value, by the way? That's going to be positive. Positive. Something's really wrong. Let's times it by 10 and see if we get something. Still can't see anything. What's distance from edge? Distance from those 2 points. Let's just point on ray. Length between the sphere, middle, closest point on ray, distance from the edge. Seems good. Because that'll always be bigger So you shouldn't go into negatives. Should we try and hard code a value? Let's say 1,000. What happens? Still nothing. Thank you, sir. You're effectively like, you know, a better version of ChatGPT. You can write the Python code for me. It's amazing. Oh, the branch disabled. Oh my days, thank you. Thank you, thank you. Oh my days, can't believe I did that. Appreciate it. No wonder why nothing sensible was nothing was working. Oh my days. Right, so it's covering the whole screen. Okay. So so that's less than. Right, so let's ABS this. See what happens. Let's just make sure it's not like some negative thing. Right, it's not negative. So let's start hard coding some values in. So let's just say 10. Right, so it's getting this sort of border right at 10. Okay, just 10. So we're 1,000 away. We're 1,000 away with 100 radius. So origin to sphere center. We kind of don't want that one. We want to use closest point on ray, is that right? Oh, shoot. Right. So trying to see how big a pixel is that was on the screen. Right. So we're trying to move that. Trying to see how big a pixel is all the way up here. So we've got this distance from the edge. Let's comment out all of this because I don't know. It's just getting in the way, and I want to see what is really what we need. So this is the size of the pixel nuclear plane distance. That is telling you that's the distance from here to here. Cone tracing. I'm not sure exactly what you mean, but yeah, so what we're trying to do is we're doing a sort of Rayverse sphere, but what I want to try and achieve is get some sort of close to as free as possible anti-aliasing. So we're just trying to work out how do we get a pixel around the edge of the sphere, when we have that, we can then sort of basically do a very cheap anti-aliasing, like in the same render, and we shouldn't have to do any sorting. We've worked out all of that stuff, but we're just trying to get the pixel around the edge of the sphere. It's, you know, been a bit of an issue. But yeah. So we have the size of a pixel at that depth. How do we know that's correct? Size of a screen pixel at depth, OpenGL or something. Yeah, right. Let's see if we can figure out that maths. That's the other way of doing it. So you've got, I don't know, you have like the length of this. You know, so this is 1, right? That's where the near plane is. So at this place, the size of your pixel is 1, right? If it's down here, the size of your pixel is 0.5, right? So and up here, well, the size of your pixel here should be, if it's here, it should be 2. Wait. If you're saying how big is my pixel here, yeah, it should be smaller. It would be 0.5, right? Because it's closer. So you got this pixel, and you're saying like, as you get closer to the camera, guess I'm confused myself which way around it is. So if you're sort of saying you got a so you got like a screen and you got like a pixel on the screen. As it goes further away, so you want to know in world space how big is that pixel? Like when it goes, yeah, so it gets bigger the further the way it goes and gets smaller the closer it comes. So by timesing it by the depth, so when you are here, you'll have a certain depth which produces something like a curve. And so yeah, it should be fine if it's like off by about, right. So depth divided by near plane. Oh, that's the other way around, is it? Right. Thank you, Nadillo. Appreciate it. So the crazy thing is though, is this is yeah, this is 1 anyway. Because we've got 90 field of view. Right, so the next problem is this distance from edge then. So we're meant to see a blue outline of 1 pixel. And the whole screen is blue, which means it's all less than. Right, so that's positive number. This is positive number. What's the point on ray? Is it? Yeah, it's definitely bigger in it. Yeah, so they're both positive numbers. Distance from the edge. Ray origin. Of that. Closest point along the ray. This subtract that. Closest point of the ray, subtract the center of the sphere minus the radius. That'll give the distance from the edge of the sphere to the ray. Looks pretty sensible to me. Let's comment out this and see if we get anything different. Right. So that's a vector from the ray to the sphere. Tangent projects across there. Apply it here. Closest point on ray. Closest. So distance from the edge. And then we've moved a pixel all the way to there to see how big it is at that depth. Technically, this is probably a little bit wrong. You know, the depth is probably relative from the camera. You know, the camera is at 0, 0. So, like, you know, but technically the depth is probably... it's something like that, right? So the Z, like the depth. It's not going to change anything, obviously. So it's less than the size of a pixel at that depth. Round is circle what I've seen. Yeah. It's because it's in the middle, right? Yeah, we move it towards the edge, it will distort. So I guess what I think is like, what could be wrong with this distance from edge? Like, what could be... Like, why is it so wrong that it basically covers the whole screen, right? Because as you saw, if I took away the radius, it sort of starts revealing. So if it times this by 2, this is GPU code. Maybe divide by 2 actually. Yeah, this is just the shader code, we're just trying to sort it out. So divide by 2 gets you this. That's 2. So let's just, I don't know, bring it down by a number, I don't know, 8. Still not small enough. Trying to see how much the maths is off by. I'm late to the stream. Hopefully you're getting ready for bed soon. Yeah, man. Very soon. I'm just trying to figure out what this thing is because it's really annoying. Like, I spent a while trying to get it. But we're trying to work out how to literally put a pixel size border around the edge. And I don't know, it seems like it was something quite simple, but it's just worked out, you know, a bit difficult. Right, what numbers have we got here? Oh. So what's the depth? Of the right, that's it. Depth is at 1,000, isn't it? Huh. Why do we have to divide the pixel? Issues SVGs. We're ray tracing it. It's 3D. So it's actually going to be, it's kind of flat shaded right now, so it looks horrible, but it's not meant to be a circle, right? It's a sphere. So we're ray tracing the sphere, so it'll be properly projected around the edges of the screen. We're just trying to get this border around it perfect, and I think we got it now. So 1,000 is the depth. So why, if we divide it by 1,000, no, that's wrong. That gets you 1. That's not right. Let's move it to the left a bit, or the right. Let's do, I don't know, 600. Is that fine? Right, let's move it up as well. Right, a bit too far. So as you can tell here, we've got, yeah, the perspective is correct. So it's like, it's more of an oval shape now, right? Oh my days, really? Right, should we add 50 pixels? Yeah, that looks like it's doing it's not quite perfect on some of the bits, but it's close. I guess the best way to test it is if you shrink the radius down to 10. If it still puts it around it, that's correct code, isn't it? Okay. Shrink it down even more. No, that's not. Shrink down to 5. We really got to test it out proper. Okay, it's putting it around it. Can you see it? Right, so that's exactly what we want. Okay. Man, I can't believe it took us. So this is its distance. So I don't know I'm not sure what I understand is wrong about the maths then. So that is the depth. 1,000 is the depth. If we literally replace this with depth, it will still work. Yeah. So let's just reduce this down. Pixel depth. No way, no way. We're just doing one. It just puts one in there. But we tried one earlier. And it was wrong. Because that's not in screens. I'm really confused. This divided by 1. Obviously get you depth, right? So what is depth? Gets you 1. I'm really confused on why this... What? Like, because when we shrunk it, right? No, this can't be right. Because we did this earlier. And then we sent this off, like... We made it, like, really far away or something. Hmm... And then we saw how it didn't map around the edge. So I don't know what I've got to do with these. Xy divided by x equals 1 divided by y. Maybe increasing resolution will remove the pixels. See, this is where it doesn't work, right? X divided by y divided by x equals 1 divided by y. Not sure what you mean by that. Okay, so then we did this instead, right? See, that ain't working, is it? It's not coloring. So I guess something else is just clearly wrong. Yeah, this was making... Yeah. This was me just testing how do we get this expression to work. But so I added a divided by depth on it, it worked. Kind of. It works for the bigger sphere. But when for the smaller sphere it's not working. So I was just trying to figure out what is the missing, like why is this covering the whole screen and how much am I off by? So depth divided by distance divided by depth, right? Yeah, I put that in to test why is this expression always true? Basically, why is it always that? So I try to figure out how do we get it to only fire around the edge of the sphere. 1 divided by nuclear plane distance is the same on that if. Intersecting with a depth plane shooting from the pixel corner would work. Not quite sure exactly what you mean. So, are we off by a factor of like 2 here or something? Like, does that... I'm just trying to see like what is... Right, ain't even showing up. That's like times it by 4 or something. No, it's starting to show up a little bit more. So it's probably because the vector no. Simplifying that if distance from edge times by near clip plane distance. Yeah, this is 1 by the way, because it's 90 field of view. 90-degree field of view. Yeah, but the distance from the edge is in world space. Right? It's in world space. So we're trying to map it back. Like, yes, you've simplified it. Yeah. Right, so you're just simplifying it. Oh. Yeah, they ain't sensible. See, we've done 10,000. So the depth is around 10,000. Let's try that one. No, sorry. It was the depth at here. And that's the depth of the sphere, isn't it? No, ain't gonna work. Let's try the other way around. See what happens. That's depth. This depths at the. Okay. So depth at. So I think part of the issue is. You got a sphere way off in the distance. You shoot a ray. The distance should be basically the same thing. So we, the size of a pixel at that depth is basically depth divided by 1 in this case. So we know how big a pixel is at this depth. We know that based on, right, moving it. We know how big that pixel is. Yeah, I don't think I'm gonna figure this out. I'll bail on it. So I think we'll pick up on this on next stream and see if I can figure this out. This is weird. We'll probably come back to it and realize something is painfully wrong about it, you know? Can't quite put my finger on it. But yeah, anyways, let's find someone to raid. Yeah, thanks for coming, everyone. So at least we Raytrace the sphere. Just trying to get some good anti-aliasing on it, you know? But yeah. Right. So we'll next be on Tuesday, 6:30 p.m. GMT +1. And yeah, so this guy usually works on a software ray tracer. Hopefully he's working on a software ray tracer. Oh, sorry, software rasterizer actually. Hopefully he's doing the same thing. Yeah, and then also stream on Thursdays as well, 6 p at 8 p.m. GMT +1. But yeah, thanks for coming, everybody. Have a great start to your week, and I'll see you all in the future stream. Right, catch you later. Bye bye.